All right, so if everyone is ready, I think we'll get started. Good afternoon, everyone. My name is Mia. Oh, hello. Oh, sorry. Good afternoon, everyone. Thank you very much for attending today's symposium on robust cyber lifeline for future society. My name is Mia, and I will be your host and moderator for today's session. It's a pleasure to be here with you. I'm just going to briefly outline the schedule for day 2 of this symposium. We're going to be divided in 2 main parts, and each section will have special lectures and then a follow-up panel discussion regarding those lecture topics. In part 1, we will have special lectures and a panel discussion organized by the Special Technical Committee on Cyber Lifelines, a Type 3 research committee of the IEICE Communication Society. In part 2, we will feature lectures of the JSD Aspire program of the Japan Science and Technology Agency. And please note that the program today will be conducted entirely in English, so we thank you for your understanding. Additionally, there is a slight change in today's program. Professor Matti from the University of Oulu, who is scheduled to join us in person today, will be attending online. So we apologize for the sudden change and thank you for your understanding. We hope you will enjoy today and the program. Please stay with us until the very end. Thank you. Okay, so I'd first like to ask Professor Nakao, Director of the Next Generation Cyber Infrastructure Collaborative Research Organization and Professor of the Graduate School of Engineering, University of Tokyo, to make opening remarks. The floor is yours.
Hello, everyone. I'm glad to welcome you all. And yesterday, we have a half-day program, and we collected more than 100 people yesterday. And if you look at this program, we had great talks by local people and also variety of researchers. And today, so we would like to do, as Mia's introduced, we have 2 parts. And the first part is special lectures by technical committee of the Cyber Lifeline. And the second part is by Aspire project program. So before we start, I would like to show this picture to you. Let me pull up. Was a great view of Mount Fuji this morning. And if you are lucky enough to see this great view of the mountain, so this cannot be seen anymore. So it's covered by cloud. So if you wake up early in the morning, and the rumor says that you can see this great view again in the evening. So maybe after this program, don't sneak out. After this program, you can have this great view again. So the reason why we organize this symposium at this very spot is that I like everyone to experience. This is a place that we need a telecommunication. And yesterday we talked about, in Japanese, we talked about lots of limitations in this area. But today, I would like to collect the wisdoms from 2 groups of people. And the first one is lectures by a Cyber Lifeline Technical Committee. And we invited distinguished guest speakers from robotics, from devices, electronics, and also a theoretical field, and also vertical player, the Tokyo Metropolitan Express Highway, and also the researchers, volcano research, volcanic disasters research. And then we can have a panel discussion after that. So the behind this Cyber Lifeline Technical Committee, I'd like to introduce this committee a little bit. So I'm chairing this organization. This is pretty new organization, and it spans across many fields of studies, and it's called a Human-Centered Cyber Lifeline Technical Committee. So a bunch of people here are shown. I don't have time to introduce them, them all, but just to, this is very small. But this is, the cross-field technical committee ranges from, various smaller technical committees and also societies. So invite Professor Nagata, Professor Watayama Sensei from a different society. So this is a cross-society activity. And after that, we have Aspire project. So Aspire is a project funded by JSD, and this main purpose is to invite people and move people around across continents. And today we have invited Matti Latva-Aho and Manu Gosain and Tommaso Melodia. So these people from abroad and all the way came to Mount Fuji region. I hope you enjoy and you can take a look at what's happening right here. And we can discuss on this very spot. And we invite Otsuki Sensei. So he's a leader of another Aspire project, and we can discuss Aspire to Aspire initiatives. I'm leading my own Aspire project, and he's leading his own. And then later we can have this discussion, panel discussion. So I'd like you to all enjoy. And so this is recorded and probably redistribute to the people who cannot attend this conference. Okay. And so now, I should not forget, Yamanaka Sensei is coming right now to give a remark. He's a PO of Aspire project. So, and then we close. Okay, so this is the brief overview. Let's enjoy this program. Thank you very much.
Thank you very much, Professor Nako. So we have quite an exciting program today. So without further ado, let's proceed to the first lecture by Professor Hajime Asama, project professor at Tokyo College and professor at the Graduate School of Engineering, University of Tokyo, to speak on distributed autonomous robotic systems, robot swarm cooperation, and self-organization using communication.
Okay, thank you for your introduction. Good afternoon. I'm Hajime Asama from the University of Tokyo. First of all, I'd like to thank Professor Nakao and all the organizers for inviting me here. It's my great honor to give a talk here. My background is robotics. Today, I'd like to talk on distributed autonomous robotic systems, both swarm cooperation and self-organization using communication, which is one of the topics I have been working on for a long time. Actually, I'd like to briefly introduce myself. I have been working on service robotics to meet the social needs by solving societal problems such as aging, safety, and so on, and to create new value. So we have worked on some development research for interacting with human, such as distributed autonomous robotic systems, ambient intelligence, teleoperation, and field and service robots. But also some fundamental research for understanding human, such as human motion analysis and modeling, embodied brain system, sense of agency, mutual stress, mental stress estimation, and application research for usage by human, such as elderly assist, rehabilitation, disaster response, decommissioning of nuclear power stations, and so on. Okay, today I'd like to focus on distributed autonomous robotic systems. So for rescue or planned maintenance, medical healthcare, the environment where the robot system is used is very unstructured. So some kind of intelligent function is required to do this kind of any kind of tasks in such kind of applications. So it should deal with some kind of diversity of tasks and environment, or we need to realize some functions of adaptiveness and robustness, fault tolerance, and so on. So our approach is the distributed autonomous robotic systems, where we use the robot swarm, which is a kind of multiple robotic agents, which can communicate with each other locally. And so let me explain some very example task for such kind of distributed autonomous robotic systems. This is a kind of object pushing tasks. So mission is to push all the object in the environment to walls and clear the room. It's a very simple task, but there are some assumptions. So robots should be multiple, and number of the object is also multiple. And there are two kinds of object. One is a light object, which can be processed by single robot, and a heavy object, which should be processed by collaboration of multiple robots. And it is very interesting. So robot can handle the light object, but if he meets the heavy object, he need to organize a kind of team to ask for some kind of help of other agents and to process the task. This kind of situation dynamically arise. That is the point. So to do this kind of task, there are many problems which should be solved, such kinds of management of task processing status, task assignment, team organization, and so on. So today I have not so much time, so I'd like to skip the details. But what we should consider is that the functions for cooperation can be divided into two types. One is a kind of collaboration, which is cooperation of robotic agents that work for common objective to help each other. And another type of cooperation is conflict resolution, that is cooperation of robotic agents that work independently to avoid conflict. Actually, I'd like to skip the details, but the point of the algorithms for cooperation is to, call for the cooperators, but we need to avoid some kind of deadlock situations. So we realize some kind of object pushing tasks by such kind of mobile robots. I'm sorry, I cannot play these movies. But anyway, so they process the object autonomously, but according to the situations, they can organize some kind of collaborative teams to process the heavy objects. So these are some kind of technology for distributed autonomous robotic systems. One is cooperation, and the communication is also necessary for cooperation, and the mechanical design for cooperative robots. And also we need to develop some kind of communication or sensing systems for cooperative robots and human interface for multi-robot systems. So this is the mechanical wheel we developed for the holonomic omnidirectional autonomous mobile robot. So holonomic omnidirectional mobility is very, very important for cooperative robots. And we developed also a kind of communicable infrared sensory systems where the robot can, exchange some kind of information of robot's ID or motion data by infrared communication when they meet each other. So this is the system. So by using this kind of systems, we developed some kind of mutually collision avoidance systems by exchanging some necessary information and applying some kind of rules which are obtained in advance by machine learning. And this is another devices we developed, which is called intelligent data carriers. So for the swarm cooperation, so if you look at some kind of ant systems, they utilize some kind of pheromone systems for local communications. So pheromone is left by some agent, and it is picked up by somebody else. And the information is stored in the environment, and only by using local communication, they can say, share the informations which are obtained by the agents. That is the key concept. So we developed some kind of electronic pheromone, which is called intelligent data carrier. The orange boxes are intelligent data carriers. So a robot can carry the multiple intelligent data carriers and put the environment and store some kind of information the robot acquired for other robots. And then he he can leave the place. But if some other robot visit the places, they can pick up the information from the environment which are stored by the other robots. That is the concept. So this is a kind of the animations. So the information is stored in the environment. So a robot can store the information in the environment or pick up the information from the environment. They don't use any direct communications. But even if you share the information by this kind of devices, robot can make a kind of very efficient motions and process the tasks. That is the concept. So this is the kind of devices we developed. And this device was also developed for the victim search purposes for rescue. And it is called the rescue communicators. And by using this kind of rescue communicators, we could realize some kind of systems which can collect some kind of voice information of the victims, which are trapped by the collapsed buildings. So if you store the intelligent carrier in the environment, and if the earthquake happened, and if the people are trapped by the collapsed buildings, these devices talked to the victims, and if the victims say something, it is recorded on the devices, and then by the constructing ad hoc sensor networks, this kind of information can be shared. Or if you operate a kind of blimp systems, this information can be uploaded to the blimp and collect the voice information to identify the location of the victims autonomously. So this is a kind of the prototype system we developed. This is the intelligent data carrier for the rescues. So maybe I'm sorry, the voice is not played here, but yeah, it is now talking to the victims. Victim is here. So he is talking like, help me, then it is recorded. And then after we operate the blimp system, this the voice data is uploaded to the blimp. Okay, so the when you design multi-robot systems softwares, so the big difference from the single robot is that the robot can get some information not only by sensors, but also getting some information by communication, which is sent from the other robots. And also another point is that the behavior of the robot is not only to move, but also to send some message to other robots. That's a big difference. So that is what I call self-expansions. So which means the communications allow robotic agents to extend expand the function of itself or embodied self beyond physical constraints. So the robot, if the robot make a kind of teams, the robot can utilize the function of other teammates. So it is a kind of expansion of body, degrees of freedom, or expansion of brain, or expansion of performance. And that is, made possible by the communications. So recently we are working on the Moonshot project. So this is a Japanese government project, and there are 10 goals. And I'm involved in the program of Goal 3 program, which is the realization of AI robots that autonomously learn, adapt to their environment, evolve intelligence, and act alongside human beings by 2050. And I'm a member of a project of the innovation in construction of infrastructure with cooperative AI and multi-robots adapting to various environments. The project manager is Professor Keiji Nagatani. And I'm in charge of robot technology for dynamic collaboration. This is a kind of concept of dynamic collaborations. So all the construction robot swarms make a kind of construction cooperatively. And there is a kind of human operators which can interact with the robot swarms. And so what we'd like to realize is a kind of very dynamic collaboration. So if we have multiple robots, the one extreme structure is a kind of fully independent and parallel systems, which is in the left side. And the right side, so that is also another extreme structures, and the system is totally has a centralized or hierarchically structured, and it is like a kind of army. But what we'd like to realize is has a middle of the has a situations. So according to the situations, robots can communicate with each other and form a kind of teams to do some kind of collaborative task. And we has a apply some kind of has a algorithm we have developed, and this is a kind of architectures of the each robot for for the dynamic collaborations. So I'm sorry, I have not so much time, so I'd like to skip the details. But this is what we realized. So this is as a experiment was done by Professor Takei, and these are some kind of the backhoes or say chlorine dumps and so on. And they made a kind of teams. So one shovel car and two chlorine dumps are a kind of teams, and to has a process the soil and transport. And but if a chlorine dump is in failure, they modify the team structures accordingly. So recently, we are developing also a kind of human interface for this kind of robot swarms. And we utilize some kind of a generative AI, so LLM or VLM, for the communication between operator and multiple robots. And it is very interesting to see, and one of my students is postdoc is working on this kind of systems, and very interesting has a function can be realized by this kind of generative AI nowadays. So I'd like to summarize my talk, and these are the take-home messages. The application of robot technology is expanding into service sectors where adaptive behavior in undefinite or unstructured environment is required. And distributed autonomous robotic systems are an effective approach to realize adaptive function. And cooperative and self-organization of team using communication is essential for the distributed autonomous robotic systems. And digital transformation, including AI and 5G or 6G, must be very relevant technology for the cooperation and self-organization. Thank you very much for your attention.
Thank you very much for your presentation. It is well taught that natural phenomena can be used in computer science, but it was especially interesting to see how the more direct replication of ant pheromones can be applied as intelligent data carriers, and to see how this new sort of communication can take a robot's capabilities outside of its physical constraints. So thank you very much for that.
Thank you.
Next, we'd like to invite Professor Makoto Nagata from the Graduate School of Science, Technology, and Innovation, Kobe University, to speak on security-oriented electronics cross-field research activities. Professor Nagata, please go ahead.
Me to this very unique the symposium at the quite unique place of the Mount Fuji in front of us. Quite a nice place. I'm really enjoying, and I'm quite surprised why we have such the area here. And yeah, Nakao-san good at the formulation of our workshop at this place. And I do want to talk about something. I'm trying to things be relevant to you, right? That I'm working mostly in the area of the hardware, especially in electronics, and what's the our common interest here. So that this is, I try to give you some ideas so that I don't know, you may make some questions or discussions to me. So here is a kind of a positioning. I'm working more on the semiconductors integrated circuits that can be designed for realizing any kind of a system applications, specifications coming from the request. But at the same time, we always need to consider two different aspects. One is electromagnetic compatibility. This is actually quite a kind of a radio things. And this is also be a part of the society of the communications. You have electromagnetic compatibility, teams. And also I'm working on the hardware security side, how we can make the IC chips to be secure, and how we can manage the things will be protected from potential attackers. Also, this team is belonging to the Wadayama-san society. So I'm myself is the president of the area of the electronics, so that I can be in the middle, right? So this is the reason why I'm here. And obviously, we have many chips in the, but this is just a slide I showed you just to capture why we have so many the IC chips here, right? In the server side, we have many processors. And also we have intermediate nodes that will handle many data coming from edge nodes, and also try to do something on edge node. In the edge node, every chips can be in your hand, meaning that you can open the chips or you can try to do something on your chip. This is a part of the security threat, right? So what's the EMC? This is a sketch. I often use this one when I'm invited for some kind of the talks. If you design a car, nowadays you have many electronics inside. Is your electronics okay for incoming electromagnetic waves? We here, everywhere, we are surrounded by the electromagnetic waves. How that would be interfered with your important things? Like here, we have a big antenna just in front of the car. This is a very special room, like an anechoic chamber. And sometimes the antenna can irradiate the big EM powers onto your car. Something might happen. What happened, I think sometimes the door will be open because of the EM waves coming from the outside. And also, these cars will emit another type of the EM noises to the other things like communication devices as well. It's a kind of the bilateral, both directions we need to consider. The noise will coming from and noise will be emitted by yourself, right? Those kind of things. And drones. I have some big industrial drones just for measuring the EM waves inside the drone. How that would be created by the devices inside the drone, and that would be interfered with communication devices, or sometimes your GPS, the positioning devices will be corrupted by the noise by itself. This is a design methodology we really need to handle such a kind of the noise within a drone. Drone must be light. You can't use a big shielding by the middle, meaning that you need a design methodology for that, right? And this is actual measurements we have done so far. It's a kind of demonstration. If you have some coil in front of the EV is in the charging, you have some wireless power transmission systems here, and you may see the noise in the very wide frequency from 0.1, 0.5 gigahertz up to the 6 gigahertz. Everywhere you have a noise. Quite similarly, nowadays we have very high efficiency power devices like gallium nitride or sometimes silicon carbide. And if you have some antenna just in front, just nearby your device, similarly, you see the noise up to 6 gigahertz. This will be straightforwardly interferes with your device. From EMC point of view, people are talking mostly about the distance about the meters, like 5 meters by the definition. But your device, everything was packed within 10 centimeters, very closely interfered to each other. This is an issue between the electronics and the communications. I would like to change the topic to the security side. You may have the many cryptographic devices on your device. And also nowadays you may have a different functions you don't expect, kind of the hardware trojans that can be situated in your device. This is a kind of a story. I think anyone don't want to believe kind of the things, but we don't have the way to prove. You don't have any hardware trojans in your device. No one can prove this. So this is another point to be discussed. And the dubious IC chips are nowadays in the whole world. In the IEEE, back in the 2013, they have a report on the fake semiconductor chips. And also regularly you have such the reports from SAE. This is the special people for the automotive areas. And also World Semiconductor Congress, they have also white papers about the potential counterfeit parts in your supply chain, right? And also in Europe, ENISA, this is the security agency. They annual reports, every year they are reporting what level of the threat you would have in the supply chains, not just for the hardware, but also for the services and the softwares as well. They have a complete research about the potential, some wrong things in your supply chains, right? Okay, so one of the policy we are discussing in electronic society, like our semiconductor design teams, like in my domain, that this we really need to have the industrial policy to reinforcement of the semiconductor manufacturing capability. I think this is a large trend, right? CHIPS Act in US, CHIPS Act in Europe, they're always trying to fund the money to the bigger the manufacturing portions to make sure that you can get a sufficient number of the devices in your area. If the shortage happens, something happens. So in Japan, domestically, the government try to invest in this part. But we, at the same time, we need to have some business environment technologies like how we can assure your device is okay, how we can eliminate dubious devices from the markets. And also we need to have the research investment about the technology, new technologies to assure or to make some good assessment of your device, reliability and also the authenticity as well. Okay, so just this is a kind of the combination of the EM and the security. This is if you have AD converters. I think that most of people think that security is in the digital domain, but it's not true nowadays. People try to make their attacks on the analog devices as well. Here is your AD converters in a car. Sometimes the sensor input will be coming to the AD converters, and if that AD converter is end as an attack, something will happen in your device, in your car, right? So this is a kind of the demonstration if that works well. Okay, disturbance injection on the car device. Here we have a CAN. This is a kind of the connection network between the devices within the car. And if we have a kind of the injector on top of the device, this is connected to the car emulator. And in the case of the regular, nothing protected, something happened, your car might be, of course, this is a simulation, something happened, your car will be broken because of the attack if something happened to your device. But if we have some secure AD converters, this is the design methodologies by the device people, and if that some intentional disturbance is coming, but we don't see anything. So now the car becomes safe. This is not the cost. If I say this kind of things, people really easily say that, oh, dear, security could be a cost. how much money you need to protect the device. But nowadays, it's not the cost. This is the kind of your device have the good position among. It's a good way of make your device quite good in the competition to the other device makers. So summary. So now I talked about the safety and security, and this is the kind of the multidisciplinary knowledge among the community of electronics, fundamentals, and also communication, so that we can do something together. We have many common terminologies like hardware-oriented security, trustworthy semiconductor technologies, design methodology of the cryptography usage and implementation, secure supply chain, and logistics management. Thank you. Thank you very much.
Thank you very much, Professor Nagata, for your presentation on security-oriented electronics. Next, I'd like to invite Professor Tadashi Wadayama from the Faculty of Engineering, Nagoya Institute of Technology, to speak on Towards Interdisciplinary Research for Resilient Communications.
Good afternoon, everyone. I'm Tadashi Wadayama. I'm currently ESS Society President. So this talk will be given from the perspective of the Society President. This figure illustrates the construction of the IEICE and ESS. IEICE consists of several societies like ESS Society, CS Society, ES Society, and IS Society, and so on. ESS stands for Engineering Science Society. ESS covers fundamental research on engineering science. This society includes around 4,000 members. And also the ESS includes the following technical groups, such as circuit and systems, VLSI design, signal processing, and so on. Okay, I'd like to move to the main content of my talk. The left-hand side, I show you the very simple sketch of the cyber physical space. The cyber physical space will be indispensable part of our lives in the near future. But as you know, there are so many threats to cyber physical spaces, like unexpected system trouble, natural disaster, like earthquake, climate change, typhoon, and so on. And also, we must worry about the cyber attacks and warfare and so on. So the safety of the cyber lifeline becomes more and more important in the near future. The resiliency of communication system against such a threat is a key issue. Okay. In this talk, I would like to focus on some topics of facets of redundancy in resilient communication. Maybe you can agree that redundancy is very important in resilient communication systems. Of course, it's true, but I'd like to ask you about the question, is it possible, is it enough? My main message of this talk is the following. Clever use of the redundancy is critical for achieving the resilient communication systems, and also numerical evaluation of the efficacy of the redundancy is also important. The history of digital communication is a history of combating stochastic disturbances like thermal noises, fading, inter-symbol interference, multi-user interference. There are many this kind of stochastic disturbance. They have been major obstacles for reliable communications in the history of digital communications. The main weapon of us for combating these stochastic disturbances are the use of the clever use of the redundancy. For example, In the case of time domain redundancy, we can use the error correcting codes. In the case of frequency domain redundancy, now we have the OFDM and so on. So clever use of redundancy is a key point for mitigating these stochastic disturbances. I'm in the information theory community, so I'd like to show you one example of the redundancy in the information theory. Redundancy in Shannon's theorem, a fundamental theorem on communications created by the Claude Shannon states that rate R less than C is achievable with virtually zero error probability. The symbol C represents the channel capacity. This is a well-known fact, but there are several hidden messages from Shannon. First one is that we cannot achieve a rate equals 1 in the case of binary transmission with reliable transmission. We must admit redundancy 1 minus R. This is a cost we must pay. And also, we have to admit complexity, computational complexity. This means that we need a long code length. And also, clever use of redundancy is very important. I'd like to show you an example. I show you two error correcting codes. The left one is a rate 1/3 repetition code, very simple one. And the right-hand side, we can see the rate 1/3 LDPC code. Both of them have the same coding rate 1/3. So both of them have the same redundancy. R is less than C. But which is better? Of course, right one is much, much better. Because the right-hand side code achieves much smaller bit error rate after decoding. So what I'd like to say is that the amount of redundancy is important, of course, but this is not the end of the story. Another important thing is how to use the redundancy is very important. This figure shows the redundancy in the computing area. We are currently using a relatively reliable digital circuit, but in old days, like 40s and 50s, the circuits are more fragile. So redundant circuit was very important to achieve the correct functionality of the circuit. So that kind of environment promotes the invention of the theory. These pioneering work gave a birth at that moment. For example, John von Neumann's probabilistic logics, and also Moore and Shannon presented reliable circuit using less reliable relays. So these works are root of the reliability theory and fault-tolerant computing. And also there is a redundancy in networks. And also for achieving the reliable communication system, data storage is very important. RAID is widely used for achieving the high reliability for storage. In such an area, Reed-Solomon codes are often used for improving efficiency. In the algorithm field, distributed algorithms are more robust than the centralized algorithm against local failure or attacks from malicious entities. This is a several example. Distributed routing algorithm, for example, distributed Bellman-Ford algorithm and its variants have been used as a routing protocol such as RIP and IGRP. And also we have the other evidence of self-stabilizing algorithm. And also in the near future, we definitely need a robust distributed AI. This is a critical issue. For example, trustworthy distributed AI need to be established. Okay, I'd like to summarize the discussion. Redundancy rules reliability. for designing a new communication system, we tend to be interested in the speed and throughput, power efficiency, cost and deployment, user experience, QoS. But however, for achieving a resilient communication system, we should be interested in redundancy and should pay appropriate cost implementing the redundancy. So redundancy is one of the key principles, but naive redundancy is not enough. So we must take care of the clever use of redundancy. And also we have to measure the efficacy of the redundancy in numerically. Because we need to optimize the system and to evaluate the appropriate cost for them. Okay, in this talk, I mentioned some facets of redundancy from the viewpoint of resilient communications. For achieving such resilient communication, maybe theory is a strong guidance to know how to use redundancy cleverly. For example, nowadays still the channel capacity created by Shannon is used for designing the wireless communication network. But unfortunately, life is complex, so theory often has been established on two simple problem settings. Theory might be useless in some cases because of the complexity of the practical system. However, I think the theory still can be a guidance in like a faint light in darkness. Okay, I'd like to summarize my talk with this slide. As I told you, the bridging the theory and practice would be very important for achieving the reliable, resilient communication system. So in order to achieve such a system, maybe a cross-border discussion would be very important. And I believe one important role of an academic society like IAICE is to promote cross-border discussion. So from that kind of cross-border discussion, maybe we have the new seed of the interdisciplinary researchers. ESS has many religion-related technical groups like that, reliability, security, information theory, and so on. Maybe strategic cooperation would be fruitful for promoting such a cross-border interaction, I think. So from this respect, this workshop is an excellent starting point towards such a direction. So finally, I'd like to thank all the organizer of this workshop for giving us this type of occasion for discussing this matter. Thank you so much.
Thank you, Professor Wadayama, and your presentation in resilient communications and in highlighting the importance of not just redundancy, but in evaluating the efficacy of it as well. I think this ties with the previous presentation, but properly evaluating and understanding costs seems to be a key takeaway as well. Next, I'd like to call for Mr. Toshihiro Koyama, Chief Facility Engineering Division, Engineering Department, Metropolitan Expressway Company Limited, to speak on challenges and future directions of communication infrastructures on the Metropolitan Expressway.
Thank you for introduction. Hello, everyone. I'm Toshihiro Oyama from Metropolitan Expressway Company. I'm grateful for the opportunity to share my work with you today. So I'd like to talk about challenges and future direction of communication infrastructure on the Metropolitan Expressway. First, I would like to introduce our company profile. Our company's Japanese name is 首都高速道路株式会社, and it's also commonly known as 首都高. We also refer to our company as MEX, short for Metropolitan Expressway Company. 首都高 was established as a public company, public corporation in 1959, and later privatized in 2005. We manage 25 routes with total length of 327 kilometers, and daily traffic is 1 million vehicles. So let me introduce the communication infrastructures on the Metropolitan Expressway. On the expressway, we have various communication facilities, such as CCTV cameras, emergency telephones, and toll gates. In order to support communication with the devices, we have established a private wired network. Specifically, we have set up an optical fiber network that connects these devices. The fiber cables are laid beneath elevated structures along the roadway. As shown in the diagram on the right, the network is designed in a ring configuration for reliability. We have many CCTV cameras on our expressways, and we need high-capacity communication. Specifically, we have about 2,000 to 3,000 CCTV cameras in total. So we have built 10 gigabit per second network for each route. First, terminal devices connected to the L2 switches in communication buildings. Above them are L3 switches and mesh devices, which form a ring network. This dual ring structure ensures stable communication to the data centers. Next, to support our road operations, we have a management radio system in place. This system uses a 400 megahertz narrowband digital communication channel, which enables voice communication between our patrol cars and the control center. It's designed to work reliably in both regular and emergency situations, ensuring that we can maintain clear communication under any conditions. However, our current wireless network faces several challenges, particularly in transmitting video and image data. Therefore, we often have to rely on commercial carrier networks for that kind of data transmission. Next, I would like to introduce our mission during disasters. It is said that there is about 70% probability of a major earthquake directly hitting the Tokyo metropolitan area within the next 30 years. Under the Metropolitan Earthquake Road Clearance Plan, also known as the 8-direction strategy, each route of our expressway network is designated as a priority clearance route. With this designation, these routes are prioritized for rapid road clearance during a major earthquake, ensuring access to and from the city center. This is because it is essential for saving lives and transporting emergency supplies. Road clearance requires the repair of road level difference and the removable of stopped vehicles and debris. For this, it is necessary to use wireless and portable cameras to check the situation thoroughly without blind spots. However, commercial carrier will be restricted by regulation during disasters. Therefore, ensuring communication methods during disasters has become a significant challenge. As a result, we focus on local 5G, next generation communication technology. So let's talk about our efforts to bring local 5G to the expressway. To achieve effective local 5G coverage along the roadway, we need to establish a narrow and continuous wireless coverage that follows the road shapes. In addition, it is crucial to minimize signal leakage into surrounding areas to avoid interference. Therefore, we have tested various antenna designs optimized for expressway. For example, we use narrow beam antennas for straight sections and distributed antenna systems for coupled sections. Let me share an example of our experimental results. In the straight section, we used a narrow beam antenna This provided sufficient signal coverage for approximately 1,500 meters. However, we observed signal leakage both onto the general roads running parallel to our expressway and in curved section. Next, I would like to present a summary of the experimental results and our approaches to addressing this challenge. In the experiments, we successfully established a linear communication area along the expressway. However, completely suppressing signal leakage is difficult and remains a challenge. To address this challenge, we have considered various measures. One example is dynamic spectrum access, or DSA. This technology automatically controls frequency and power to reduce radio interference. We have already conducted experiments on DSA and confirmed its effectiveness to some extent. Next, I will talk about efficient maintenance of local 5G. To inspect equipment on the expressways, we need to enforce traffic regulation at night. To address this challenge, this takes both time and money, so the maintenance is not efficient. To address this challenge, we developed a vehicle called the 5G Web Doctor, which measures the radio environment while driving. This vehicle enables efficient maintenance and management by performing drive-by measurements and automatic field strength mapping without requiring traffic regulation. Using the 5G Web Doctor, we aim to ensure the efficiency and reliability of our local 5G network for daily operation and emergency response. This slide shows actual measurement results. It shows the reception power at each location. By driving the vehicles, we can collect this data, which is accessible via our web page. The results can be displayed separately for the expressway and surrounding streets, making it useful for understanding the extent of signal leakage. To summarize, the Metropolitan Expressway is designated as a priority load clearance route during major earthquakes. This designation requires high speed, high capacity, and stable communication for rapid response. We have focused on the potential of local 5G to meet these needs. Through our experiments on wireless area construction and automated interference avoidance, we have addressed many of the technical challenges for deploying local 5G on the Metropolitan Expressway. Additionally, we developed the 5G Web Doctor vehicles to ensure efficient operation and maintenance of the wireless networks. Finally, we will continue to explore the implementation of local 5G. I would also like to express my gratitude to everyone who has been involved in these studies and discussions. Thank you very much for your attention.
Thank you very much for your presentation on the implementation of local 5G on the Metropolitan Expressway. I think this particularly highlights just how wide the use cases are for local 5G. And it was very interesting to see how local 5G must overcome the specific challenges posed by the Metropolitan Expressway. Next, I'd like to invite Mr. Ryo Honda from the Mount Fuji Volcano Disaster Prevention Research Center, Mount Fuji Research Institute, Yamanashi Prefectural Government. So please go ahead.
Thank you. And okay, before my talk, everybody please speak close to the mic. Okay, and okay, let's start with beautiful picture of Mount Fuji. And I took this picture just 1 month ago from the north side of Lake Kawaguchiko. And I always say, please notice the undulation, topographic undulation here. this is a trace of former eruption, and almost everybody thinks the eruption occurs from the top, but in Mount Fuji and also maybe other volcano too, eruption is occurring very lower place, so maybe near the resident place. And I talk about the communication infrastructure we require. So from the top view, the volcanic relief is like this, and you can see the eruption trace here. And this is orienting northwest to southeast. This is occurring by plate compression. And I am breaking chestnuts like this. And this is the very same thing is occurring in Mount Fuji. And in hazard map, we are showing the possible crater appearance area like this, and about 25 kilometers for length. This is so wide area, and the problem is we can't tell which place the eruption occurs. So we have to decide to evacuate which part of people, and that is a problem in volcanic disasters. And in volcanic disaster, other problem is like I shown, there is various phenomena like lava flows and ash falls, and this is pyroclastic flows and ballistic rocks. And these are very dangerous phenomena, and we have to evacuate by different means, different way from each phenomena. So this is also a problem of difficult volcanic disaster. Okay, so this is not the problem only in Mount Fuji, but by the location you are, you have to change the direction of you escape. And also, by the location of bent volcanic crater, you also have to change the direction of escape. And also, by different hazard, you have to decide you have to escape or not. For example, you must escape from lava flow. You can't stay in your home. And by ashfall, maybe this is recommended to stay at home. Maybe you're hit by car. So, variation of escape direction and means caused by where you are and the location of bent and hazard. And also, very variable phenomena. By variable phenomena, the left side map is hazard map, and right side is evacuation map. There's so much information in one figure. So this is also the problem of volcanic disaster. Okay, so now I show the example of volcanic disaster this is in Hawaii in 2018. So now I showed how it's unpredictable. In Hawaii, the eruption was always occurred in this section called Pu'u'o'o cone, and the eruption was maybe 35 years of eruption was continuously occurred. And in 2018, abruptly in maybe, you can see the scale well, maybe 20 kilometers or 25 kilometers away, there's a abrupt start of eruption in a resident area. So you can see this picture, the house is here and vent is here. And eventually, the lower left figure shows the deformation of caldera in here. So the magma inside this ground flow over from the resident area, about 40 kilometers away. And the 35 years eruption here was ended at this moment. So maybe you know how unpredictable the eruption is. So in Kawaguchiko, the top picture again, from the point I took picture, the peak was about 18 kilometers, and mountainside vent array is 12 kilometers away. And in Hawaii's case, this distance is, I don't think it's safe. But in Fuji, maybe this distance is safe, but generally, a volcanic event is unpredictable. Okay, so for the communication infrastructure, I want to say what is required. The point is there's a necessity to constantly obtain information. So we need an uninterrupted communication infrastructure for the constant information. So we, Nakao-san, are executing many experiments in Mount Fuji. This is one in the outside, you can see this buggy. And we tested this buggy plus local 5G stations and Starlink to the wave. And we tested the communication between Mount and here, our level. And in the disaster case, we can use the drone monitoring to the buggy, and Mount had staffs to the communication and local staffs to gathering information. And every information should be go to the countermeasure headquarters. So this would be a quite powerful and flexible tool. And also for the complex informations, we have to do many things. This is the figure I made. This is expressing the road status in volcanic multi-hazard. In this case, we are considering the lava flow and volcanic ash falls in simultaneously occurring. And here's a load category by different colors. Green one is usable, so everyone drive this road. And blue one is here. This is a little ashfall district, and this is not recommended to drive. And orange one is you can drive, but no way out by the destructed roads. So, and red one is destroyed road. So, in a volcanic hazard, this happens scarcely, and in Mount Fuji, there is no eruption these 300 years, and maybe no one can imagine what will happen. So the visualization is very important. And the showing complex data is very difficult, but there is a good example. This is a rain cloud radar, and you can avoid rainfall by this information. So this is very suggestive, I think. And this kind of data sharing, information sharing is quite important. Okay. So, so what is required in a volcanic disaster? First, with sufficient redundancy, and by the buggy experiment, we realized the rapid recovery is possible, and this is very useful maybe in the disaster time. So these are the requirement for the realized uninterrupted communication. And securing bandwidth that we can use multimedia communication, because animation tool is very useful to information sharing. So this will be required. And in the future, maybe fully covered is very important, because I talked to some people, this level is not so covered in part. So this will be a issue. And at the first, maybe thousands of people gathering to Mount Fuji, they will be not covered in one time, maybe, but for the future, we want to realize. So this is my talk. Thank you.
Thank you very much for your presentation, Mr. Honda. So this concludes the lecture portion of this first half. Before we move on to the panel discussion, we will take a quick 5-minute break. So please be back here by 2:20 sharp. I'd just like to also mention that we have posters around the venue behind you, where you can read on the ongoing current projects at Nakao Research Laboratory done by students there. So see you back here at 2:20. Thank you very much. The panel discussion is going to be moderated by Professor Akihiro Nakao. Our panelists today are Professor Hajime Asama, Project Professor, Tokyo College, the University of Tokyo, Professor Makoto Nagata, Graduate School of Science, Technology, and Innovation, Kobe University, Professor Tadashi Wadayama, Graduate School of Engineering, Nagoya Institute of Technology, and Mr. Ryo Honda, Mount Fuji Volcano Disaster Prevention Research Center, Mount Fuji Research Institute, Yamanashi Prefectural Government. Please, the floor is yours.
Okay,
Mr. Nakao.
so let's get started. So thank you very much, first of all, for great talks. I was so impressed. And the reason why I put together this program is that this telecommunication is so much important now. So we think that we consider that as a lifeline, and we call it a cyber lifeline. And before we start, I like to again introduce a president of ESS, president of ES, and I'm the president of CS. So we have communication, electronics device, and also theory. And there, Yamanaka Sensei is sitting. So he's a president of the whole, the set of societies. So if someone attacks this building, so we are in trouble. So And also we invite Sama Sensei and also Honda-san. So they are representing the use cases, robotics, and also disaster recovery using telecommunication. And so I have this, so before we dive into the panel discussion, I want to explain to you that why we invite these people. Because communication society treats before that, application people like robotics and also disaster recovery may not know the detail of telecommunication detail. And often cases they treat communication as a black box. And in the same way, we treat device and IC chips that the Nagata sensei introduced, we treat that as a black box. And sometimes we treat theory part, taking into, for granted, and we don't dive into the detail of the theory. So I don't like this situation, and I want to break this out, treating each other black box. So that's why I collected these people and talk about just the one topic, the cyber lifeline. How can we make the robust telecommunication system if we get together? I mean, application, use cases, and communication device and theory, right? So that's why I like to have this panel discussion. Okay, so this is the background of this panel, and we already heard a lot of interesting wisdoms already, like Wadayama sensei said that redundancy rules reliability. And also Honda-san said sufficiently redundant and a rapid recovery, capability is very important. I think that we see a lot of common wisdom that we shared. And so let me share the panel discussion. I already shared with you. So because we are interdisciplinary now, so I like to discuss what innovations are anticipated as a result of promoting interdisciplinary research and technology collaboration in building a cyber lifeline to support future societies. So so here we are in Mount Fuji, and I heard from Honda-san that we need to build the constantly information sharing and also quick disaster recovery, right? And we are here, we kick off this meeting. So what can we do so if we get together, right? So for example, I give you a little bit of my thought listening to you. For example, Asama sensei introduced the collective robots. So, group of people can get together and work together. So Honda-san, can we use that kind of robots in the mountain so that we can collect information or do things? And also, can we do from a device perspective or theory perspective to help this movement? And Asama Sensei, can we apply this robotics, your cutting edge technologies for this environment? So what is missing? What do we need to do to help Honda-san?
Okay, thank you very much. And actually, the system we are developing is a kind of a prototype system, and it works in a laboratory. So I think application to the real side is, I think it's a big challenge. It's not so easy. So maybe, of course, we should think about some kind of real communication range or some kind of say the energy or survivability of the devices, and also some kind of the reliability and some kind of how to say the environment, the setup we are using in the laboratory is a kind of how to say very ideal situations, but in reality it's very, very different. So maybe I think that is not so easy to just transfer the the technology we developed in the laboratory to the sites directly. But I think, of course, the concept would be some kind of very, applicable, but in reality, we need to solve many problems.
So I have a question. Why a single robot can solve the problem that Honda-san has? Do we need multiple robots, cooperative robots to solve this problem? Or single robot is simple enough? We can have a battery and also energy to support or just a single robot. But why do we need multiple robots?
The reason is very simple. It's a kind of adaptiveness. So maybe if something happens which is cannot be predicted in advance, some kind of adaptiveness function is necessary. So maybe redundant is one of the very important sort of concept to make it more adaptive, because so some kind of functional degeneracy is necessary when some kind of failures or malfunction happens. And so in the case of robot, it is very easy to break, but it is very difficult to make the systems not to break so easily. So some kind of more, systematic design should be necessary. And in that kind of context, the multiple, agent concept or make it redundant is very important concept.
I see. So if you want to jump in a discussion, that's okay. But I'm thinking now. So of course, everyone talks about redundancy, especially Wadayama sensei. And Asama sensei also said that the multiple robot adaptiveness. But that may add a complexity. And we have to control the group of robots. And our communication society, we make it simple, communication simple and stupid. There is principle is called KISS. Keep it simple and stupid. So this is very interesting term, but we always say KISS principle. And on the other hand, I understand that adaptiveness and the redundancies is very important. But at the same time, we have to value the simplicity, because if things break, we have to fix it quickly. So I'm wondering, by listening to Asama sensei's opinion, how can we, do a trade-off between complexity and also redundancy?
I just forgot to the one more thing. So the simple is very important. So the key point of the distributed autonomous system is to make the communication local. So if you use the global communications in a multiple robot system, it really has a hard. So maybe, so just suppose the creatures, they don't use a global communication. They use only local communication. That is a very simple solutions of the multi-robot system.
So your opinion is that we have to use the multiple robots that make communication system simple. So I actually like your idea very much, IDC. So you put information in some device and some robot comes and pick up this information and it takes over the operation. That's very nice. Honda-san, do you have any opinion about the simplicity? And because you are facing this disaster, possible disaster every day. And I think you might have opinion about the simplicity or complexity or redundancy, complex operation versus redundancy.
Well, difficult question, but first, before I thought of the robot inside the level, maybe it will be difficult in operating in outside. So I think in Mount Fuji, there's a severe condition. So I wanted to use this condition to the testament. And over the test, maybe the simple but a strong system will be im improving, or I don't know what to say, but of course, the situation in volcanic disaster is very complex. So I think first start with simple disaster like earthquakes or floods, maybe good test, maybe.
Well, of course, we can use this place as a test bed to try out many ideas. But when it happens, I mean, when eruption happens, so we need a simple solution.
Yeah, simple, but I think one of simple way is by number. Some piece will make it, and other is not. But only one piece make it. It will be enough. In a simple meaning.
So Honda-san and I are working on this local 5G and also satellite system. And the satellite system is a redundant communication. Satellite communication is very complex, but you can think of it as a simple communication, just the one link, right? But we have a terrestrial network also, and use that for redundant communication for backing up. So I think Asama Sensei, maybe what Asama Sensei told us is probably the good way to do that. Keep it simple for each communication. Keep it simple, but you have to have a multiple of them, and make operation relatively simple. But you have to have a adaptive system. Okay, so I'd like to, so if some audience has any question or opinion, please jump in. And because we have to borrow some wisdoms. Okay, so Wataima Sensei or Nagata Sensei, do you want to say anything about this?
Questions. How many sensors? How many observatory places you have in the whole area? So I would like to see what's the symptoms you would see, right? That if you have the distributed sensors, I think you may have many different kinds of sensors. And what's the answer? How many?
Now?
Yeah, now.
Yeah. Well, there's various sensor, and the basic one, seismometer, will be about 39 or 40.
Last year, my guess was kind of something more than 10,000, 100,000 larger, right? That because if you use semiconductor technologies, right, that you may have so many devices at the same time, right? You can distribute them on the RAN, and easily that will be communicated with the simplest one you're talking about, right? And the energy-wise, the solar can give you some power and the lowest energy consumptions, and some of them can work, some of them will be died out. But if you have so many simple devices that can work, what do you think that kind of idea?
First, seismometer is difficult to keep by solar energy. And for example, GNSS, GPS, like GPS is maybe supported by solar energy. So in some places, GPS is okay, seismometer is okay, but in some places, GPS is okay, but seismometer is not good.
But what about like a temperature difference? That also another source of energy.
That kind of sensor will be less energy, so that will be good. Yeah, but yeah, in many cases, electricity is the problem.
Yeah, I know. Yeah, well, this is about the point. So I think that if we have the super low energy sensing front ends that have their very simple wireless communication capability, and simply you can have the information, and you can understand what symptoms you could see from the earlier, well, from the group of sensors, kind of that.
So Nagata Sensei, I have a question. So, no, if we can transmit just one bit, 0 or 1, how low energy that you can go? Like,
Well, it depends on the distance, right?
Depends on the distance. What is the cutting edge IC chip technology here? It's because we work on the LPWA, low power wide area, but we still transmit it's not several kilobit per sec, because we like to send a lot of information. But according to your idea, very simple bit, 0 or 1.
That is kind of the on-off keying, right? Kind of that, at the quite low rate, like several passes in a minute. Kind of that could be super low energy, but it's a matter of the coding.
Yes.
So what kind of information you really need? Just the thresholding would be the easier, right? That if that starting parsing, meaning that sensor will try to tell you something, and then you can focus on that. In that sense, that you can use your power to see that one. Otherwise, that sensor node will be just to be awaking and trying to sending just the pulses. Could be quite small. I don't say that what's the energy or picojoule, or well, I don't say the energy numbers, but that would be the lowest energy case, I would say.
Is there a possibility that we can make a simple 0 or 1 transmission robot, for example, and distribute on the mountain?
Probably. But it depends on the distance. What's the distance you
Distance.
want to?
So Hoda-san, how long is this communication should be like?
So relaying 20 kilometers is possible?
I don't know. I don't say. I don't answer. But you may have just some like drones. Drones can you're flying over, and in a close proximity to the device, that the drone can capture something from that device. Regularly, the drone can. So that you need energy, but you don't put the energy on the sensors. Sensors can work quite in low power, but you can collect the information by using some other things that will consume much power, like drones.
Yes, collecting observation data by drone is very simple and attractive.
So can you use a 0 or 1 bit device? You can sense, okay, something exists, something doesn't exist. Can you use this?
Like lava flow, so if it's alive or distracted, it's 0 or 1 information. So that is a simple and detecting volcanic vent immediately. It's very simple and easy.
Okay, this is one possibility. Wadayama Sensei, can you contribute to this discussion? So I think, do you work with Nakata Sensei already or not? You, I mean, so Nakata Sensei talked about codec, right? So if you can do coding that is power efficient.
The power efficiency is an important topic for the correct coding. And the most power consuming part of the coding is the decoding part. So maybe for this such an application, we can devise a new coding scheme that requires less power consumption. But that is one possibility for future direction, I think.
So we don't have to have an answer here today, but I think if we can define a direction that we can cooperate together interdisciplinarily, so then that'll be good. Because I work on very high power, highly efficient communication like 5G. But at the same time here, it may be necessary, but at the same time, hearing what you say, maybe we should develop a very simple sensor, which is super power efficient, but which has to be usable by Honda-san, right? Or Oyama-san also. So can you work on that?
Maybe.
This is just one topic. Yeah. And also, Honda-san, is there anything that you would expect from these people? Because we have expert on communication device and also theory and the robotics.
At this time, I can't image the special one, or but I think it's important to the communication between this group and to enlarge this group, because our volcanic research community is very small. So maybe I want to do this thing. I say I want to do this thing, but if somebody listens that, maybe the group was large, somebody raised the hand, and I can do that. So that is important.
Manu and Tommaso, maybe I can use your help. Do you have any opinion about the discussion here?
Sure. So one, I think, Honda-san, I would say when you mentioned that your volcanic community is small, I think I would disagree with that, because the issues that you face, they are translatable to other application domains. So I would not necessarily, because every issue that you talked about, you're talking about the same issues that we're looking at for mobile communication systems. You want reliability, you want coverage, you want capacity, and it's just a different, domain. So I would put that or categorize your work around public safety, and put it in a broader picture. So I would say that it's not a small community. So I want you to feel encouraged that these are the problems that not just you and your research domain is facing, but it is something that we are looking at, and when it comes our turn, we'll give you some thoughts on that. I think the interesting concept, Nagao-san, you talk about, which is the energy per bit, and that's quite interesting, because that is, and then the other part that I want to talk about, which we haven't heard yet, is integrated sensing and communications, which is a upcoming topic area for 60, and that's sort of where our session will be looking ahead. So these are kind of the input requirements that we want to see. So that's probably something that would be very useful for you, if you can use the same channel to sense and to communicate. And then as we build more efficient coding schemes, as we bring on the opposite side, because right now our issue is we want more MIMO, we want more capacity, we want terahertz. But I think right now the biggest issue is around reliability, and how do we get the bit from where you need it to where it sort of needs to go. So there's an architectural rethink that needs to happen, and that also needs to be looked at from the perspective of, how do you sense? Because at this point, you're trying to sense the environment. And if you don't have physical sensors that you can place, how do you use some of the ambient information? How do you use noise? And how do you use, those information bits? So I think that's interesting, and we'll share some perspectives looking ahead.
So do you have any US activity on this, like the single bit sensor and a very super efficient and power efficient sensor?
Not on the sensor side. I think we're looking primarily power and energy efficiency more on a macro network scale. So that sort of, but I think, yeah, sensors maybe.
I think there's a lot of activity in the US on zero power sensors. So sensors that are activated directly by the phenomenon, by the physical phenomenon that they're trying to sense. Specifically, there's been applications to Northeastern has had a few projects on ultra low power sensors, zero power sensors for detection of fires, basically. So where the fire signal itself gives power to the sensor to communicate wirelessly the information. That's a very, very interesting topic.
Okay, so how many bits can you transmit by using this zero power sensor?
believe they're basically sensing temperature. So it's a few bits.
That's simple,
Yeah.
simple one. Yeah, good. So as Manu said, we are working on communication and sensing at the same time. Maybe in the next session we can talk about it. But so thank you, for answering. So Honda-san, maybe as Manu said, we should expand. I mean, we are talking just about Mount Fuji disaster recovery, but maybe we can extend it to different field, right? Okay. So, okay, so any more opinions from, if you can contribute this interdisciplinary approach, can do that. So I'm happy to see that there is a common term, redundancy, came out, right? So in theory, so Wadayama-san is talking about redundancy. Maybe we can extend a little bit about redundancy. Nagata sensei, do we have a redundant device or what?
Redundancy is always there in the devices, like especially for the automotive. Right? Every decision should be made by the 2-3 different processing elements for the final decision. This redundancy is always be built in the system.
I see.
So I really like that idea.
So we don't have a redundant sensing or redundant communication just yet. We have a very simple system in Honda-san's system, right?
I think that here, as I mentioned, if we have so distributed sensors, by nature, it can be redundant. You see their statistics, how many devices will be responded. And if you see the many devices responded at the same time, something happened. This is the kind of inclusive redundancy.
Okay. So maybe we can, next time we can extend this and we can make a redundant huge number of sensors distributed over mountain. Is it possible, Honda-san?
Maybe we have to discuss this about this with Ministry of Environment. Or
yes, so we have so many limitations here because we can't do things freely. Yeah. Okay, sure.
But from the security perspective, sometimes those devices be biased intentionally by the external power, right? That you need to have the security aspects at the same time. Otherwise, the people will be faked.
Yeah. Yeah, yeah. Okay. Yes. Okay. So who is going to make a draft of this? Honda-san, maybe you should take a lead.
okay, I will try.
Okay, so now we are close to the end of the panel. So I'd like to address this second point. What is the practical measure should be undertaken now to build a robust and resilient communication system? One answer is that we discussed already that very simple communication, simple sensor, power efficient sensor distribute a huge number of devices over mountain, and this is a proposal, and Honda-san is going to take a lead on the draft. Okay, so any other things? Let's go one by one, and what can we do? Or for example, what if we have this panel next? What can you promise to them? Honda-san, you can write a draft, okay? Wadayama sensei, have you thought of anything by listening to other people? What can we do?
Actually, I'm from theory field, so I have no strong opinion about the practical things. But what I'd like to say again is this kind of cross-border discussion would be very important for the next innovation about resilient communication. So having this kind of occasion is very nice. At least I can say.
Yeah. From your slides, Manu and I, were, looking at each other's face because we know LDPC, we use LDPC, we use Byzantine fault tolerance. Lots of theory are used in communication system, of course. I think we should work more between communication society and the theory society.
Maybe still we can learn from old theory, even in practical cutting edge system. So maybe there is something important can be found in the theory.
Nagata Sensei, do you want to say anything?
I can't promise, but I think I can show you some chip architecture that how that could be fit well for this kind of the applications.
That's good. I take it as a promise.
But I'm saying this is the kind of the architecture. If you want to ask me to build the chip, that would be a different part, right? That I can show you some the block diagram and what the power should be consumed by each of the block. That can be a kind of the analysis part. But if you do want to make some demonstrations, that could be another part, right? That we need to design and fabricate the chips that I'm always doing in my lab, but it's be the different story.
Let's keep discussion. Okay. Asama Sensei, do you want to say anything? Can you contribute to this group of people?
Okay, I'd like to mention one thing which is now happening in Fukushima. In the say decommissioning site of Fukushima Daiichi nuclear power stations, they are using now multiple robots. Okay, so especially they use 2 robots sometimes, and one is used for some kind of tasks, such kind of how to say investigation or just sensing or just handling some kind of materials. And one is used for relaying communication. So the has a wireless communication is quite important in such kind of very complicated environment because wired communication needs some kind of how to say handling of the cables, and that is really how to say annoying. So how to say the environment is lots of have lots of the obstacles and walls, and it's really difficult, and some kind of how to say systems which relay the communications to how to say make the wireless communication possible is necessary. So maybe it means that the robot can be a kind of how to say a device which how to say move around in the environment to how to say change the communication how to say the structures. So maybe making use of this kind of how to say the use of the robots might be some kind of how to say broaden the possibility of the communications.
Thank you. So I'd like to close this panel, but before that, because you have seen the Honda-san's problem and this region, what it is like today. And I have been trying to contribute my expertise to solving this problem. And I'd like you to join this team and from a different angle. And this is the very reason why we formed a team of this Cyber Lifeline Technical Committee. And please consider very seriously that what individual player like us can contribute to solving this issue, because many people are suffering from a climbing accident every day here. And we haven't done much. It's just close to center of the Tokyo. It's just 1.5 hours away from the center of the Tokyo, but still we have this incident happening. Please consider this opportunity And let's thank the speakers and also panelists. Thank you very much.
Thank you very much for the panel. We are going to take a quick break and start section 2 or part 2 from 3:05. So please return here sharply in about 7 minutes. Thank you. Okay, I'd like to get started with part 2. We have quite a few interesting lectures, so if I could invite everyone to please sit down. I'd like to invite Professor Matti from the University of Oulu, Finland, and director of 6G Flagship, to make his presentation on the 6G for the good of society. The floor is yours, Professor Matti.
Thank you. Thank you, everybody. Thank you for the invitation to give this speech. Unfortunately, I couldn't make myself to travel to Japan
Sorry
this
to
time.
interrupt. We're just having a bit of an issue with the audio in the room. Please give us a quick second.
Okay.
Great, sorry about that. I think we can hear you now. If you could try.
Can you hear me loud and clear?
Yes, we can hear you. Thank you.
Okay, so I'm going to talk about some of the issues that are not so frequently discussed when talking about 6G. I'm going to talk about some of the societal challenges and why we should also keep those in mind when going to develop the next generation standard. And when we look at how different mobile generations have been developed from 4G, from this left side, always best connected, and then to 5G, including machine type communications and Internet of Things. And now with 6G, we have been mainly focusing on enabling 6G metaverse and digital twinning, really sophisticated applications. But we are not talking so much on what are really truly the societal needs. And currently, as we understand, resilience is one of the big issues that needs to be addressed more. Sustainability development issues, they have been in political talks, but not so much reflected yet on actual technical research. And of course, for sure, we all know that AI is going to change the way we are developing different sophisticated applications and even how the underlying technologies are working in the future. So AI is definitely something we have to address much more carefully as well. We do believe that we should pay much more attention to what is exactly needed in different vertical applications. And one thing related to this is that traditional mobile network operator business has been focusing on creation of mobile broadband connectivity mainly, which is of course super important, and we all are thankful for them making those happening. But I think we should more start to think about what are the societal and vertical needs. Different verticals are of different nature. The communication requirements are very different. The business landscape is totally different. So we should understand that far more better and try to involve them in developing the next generation standard, rather than pushing fancy technologies and saying that, yeah, we have this great solution, use it. Alongside with mobile network operators, we need new players, and we have been talking about private and local operators in collaboration with Tokyo University for some time, where we are trying to foster development of some of the critical technologies that will make those happening. Customized solutions are needed for different vertical applications and areas, and one example of this customization platform is this O-RAN type of platform, software configurable networking, which is really going to change the world pretty much and enabling us to really optimize solutions for different needs. regulation policy is very important to enable a development of these different vertical application areas, and also offering, for example, spectrum for operating those networks in the future. So flexible and innovative regulation policy is really important to make this happen. Currently, when talking about a little bit about the spectrum issues, we were thinking 6 years ago when we started our 6G flagship program that these high spectrum bands will play a major role when going towards 6G era. But now it doesn't look like that anymore. So everybody is talking about these FR3 mid-band spectrum, 7 to 15 gigahertz spectrum area, where there is still some possibility to try to deploy mobile networks there. But once the technologies are getting matured for high spectrum bands, for 100 gigahertz and even above towards 300 gigahertz frequency bands, then we have really powerful tool of making all sorts of local networking solutions, offering super high capacity for making, for example, these metaverse type of applications really easy to implement, and also spectrum wise easy to handle interference and so forth. So maybe that comes a little bit later, not in the first wave of 6G. So most of us at least, we are well aware of these IMT 2030 usage scenarios. So these green ones are the old ones that already existed for 5G development, and the blue ones are the new ones. So we want to involve sensing as a part of communication networks. We want to have really deep inclusion of AI algorithms and AI methodology to be part of next generation mobile networks. Also, which is obvious that since our societies will depend, and we as humans, individuals, we depend so heavily on mobile network connectivity, ubiquitous connectivity becomes really vital for the future. So what all these things will mean, and what are we doing, for example, which is a little bit out of the box thinking related to these integrated sensing and communication solutions. We don't see it only as inclusion of accurate localization techniques to mobile communication network or as a part of data communications. We are focusing, for example, looking at multimodal sensing technologies where we integrate LiDAR and video imaging to radio positioning, radio localization, to enable different sorts of sensing capabilities in the network. And so we have to keep a little bit open mind on that. And we do have lots of video cameras everywhere in built areas, and LiDAR technology is becoming cheaper and cheaper, making this really viable solution. This entrance of AI to radio access networks is potentially revolutionizing, and Open RAN is potentially revolutionizing the whole market related to mobile networking. The grand nice idea is that we just define interfaces, and anybody in principle can provide different functional blocks to radio access network. Well, maybe that's more easy to say than realize in practice. These interoperability issues are challenging, and lots of practical issues related. But we are going to move to that direction, and one day we will have this as a reality. So when that is available and ready, first of all, the whole mobile network market is totally different, and then we have great powerful platform in trying to offer customized solutions for different vertical needs. Ubiquitous connectivity is let's say it's more as a financial issue than technical issue. If we had all money available to build these networks densely enough anywhere we want, we just build up base stations and that's it. Unfortunately, it doesn't make much sense financially to build base stations in sparsely populated areas. And there are also quite limiting factors from natural terrain, like mountainous areas like Mount Fuji. So maybe we have to also start to think more seriously than before the utilization of satellite technology to provide connectivity to remote areas. Unfortunately, satellite technology is not that cheap at all. And we have several billions of people living in poor countries and areas, and they really simply cannot afford to utilize satellite. So we still have to keep looking for alternative solutions for even rudimental service levels for remote areas. So resilience. So when 4G and 5G were being developed, we were mainly looking at how we can make more efficient mobile broadband networking, or how can we involve machine type communications very efficiently to be part of 5G network. Gradually, when we started to do 6G research, we have been starting to talk about sustainability development issues. So there are these 17 UN SDGs, and we can try to utilize our technology skills to solve each and every one of those. Probably the most burning issue in sustainability related discussions is energy efficiency. So currently the mobile networks are consuming more and more energy than the previous generations. Of course, the energy per transmitted data bit is going down, but we are transmitting more data through mobile networks, meaning that the electricity bill is increasing dramatically, and operators don't really like it, and they're really crying for lowering the energy costs in operating mobile networks. So there are lots of things that we have to look at in energy efficiency. Another example of sustainability development targets is really the ubiquitous connectivity. It's really every man's human right issue already, that everybody should have access to internet and access to information that is available there, the related services. So resilience is a new kid in town, in the sense that we haven't been talking about that so much. We know that we have increasing amount of natural disasters everywhere because of climate change. For example, yesterday we had snowstorm in Finland, and in southern Finland, many places we had major power outages, and also lots of mobile networks were down for several hours because of lack of electricity. And we can really definitely do things to try to avoid losing the mobile connectivity in the case of power outage very easily. I will show you some examples later on. But we have to pay attention to that. Also, the world is currently, at least, unfortunately, much more hostile than it was a few years back. There are lots of crises ongoing. There are wars here and there, which is really causing lots of pain and suffering to civilian society. And one thing that is also affected is, of course, mobile networks. They are really knocked down, but things don't need to be like that necessarily if we take into account resilient by design principles early enough in making sure that the mobile networks can operate also in a robust mode when something unwanted happens, something unexpected, something that we cannot even plan for beforehand happens. So the basic challenge is actually that these unwanted events happen very rarely. We don't know when they happen, but they do happen every now and then. So the big question is it worth of investing money to try to protect ourselves against those things? So this is really a key thing there. One example of an interesting recent works is coming from Germany, from this Open 6G Hub from University of Kaiserslautern, who are leading it. They have recently published a paper on resilient by design concepts for 6G, where they have really broad concepts, and as you can see from here, is that resilience is really broad. I mean, they can look at it from different network layers perspective, from services all the way to electronics, and it means different things in every layer. We can look at how these are related to other critical infrastructures. Very easy to understand, for example, the energy infrastructure. Also, there are different, let's say, phases or plans they want to try to suggest is some protective measures on top, then increasing the awareness of malfunctions in the network in the middle, and then on the lower part is reaction on the needs of changing something in the network. So this is something which we haven't studied intensively enough yet. Of course, in control theory and automation sector, this is probably an issue that has been looked at in various different ways in past. But when we introduce these things to wireless networks, because the wireless media is somewhat unpredictable, we are introducing lots of really interesting research problems, and we are going to look at quite a few of those. My last slide, which is basically paving way towards the later panel discussion as well, and examples, very simple examples of what could we do in short, medium, and long term. And in short term, for example, if we have some network failures happening in mobile networks, we could very simply force national, not natural, but national roaming amongst operators. So if one operator network is having problems, maybe all users could utilize the services through another network offered by another operator. Then in medium term, we could try to push, and we could, as a research community, keep making more noise that standardization processes in 3GPP, they should really take seriously resilience-related issues, and they should really have a clear roadmap how to start to address these things in different releases of 6G standard in the future, starting from simple, easy things to do, going towards more challenging in the future. Then the long-term issue is what I've been thinking recently, is that how can we protect ourselves against power outages, and what should we do? How should we reconfigure the network against power outages? And the key thing is, I think, that we should define different operational modes, a safe mode to normal mode and anything in between. For example, if we lose all the power, we still have the battery backups at the base stations. The question is, how should we utilize these batteries in the case of losing the power grid? I don't think we should let the network operate in normal mode, allowing video streaming, etc. It should be operated in safe mode, prioritizing traffic for emergency services, and also allowing public authorities to use it other than anybody else. And then the last thing is the example that which is kind of threatening to me, that by 28, in few years time, Finland will give up the office of public officials' private wireless network, and they will start to utilize a commercial network for delivering public officials services. So if public mobile networks are down, they don't have anything else than the good old VHF radios available, and this is not good development. Thank you.
Thank you very much. Thank you very much. I think resilience is a word we've heard several times today, so hopefully that is something that we can delve into more during the panel discussion. But I'd like to move on next to our next presentation by Mr. Manu from Technical Programs, Electrical and Computer Engineering, Northeastern University, to speak on resilient future communications enabled by open radio access networks. So if you, please, you have the floor.
Sure. Would you be able to bring my slides up?
The slides.
Okay, so just in the interest of time, while the slides are coming up, I'll just go ahead and get started. So I'm from Northeastern University. The perspective that I'm going to share, we have a follow-on talk from my colleague who will be up next. So we'll talk a little bit more about open radio access networks. My perspective on resilience is going to be through the roles that I have primarily supporting the US, United States government, two separate agencies. One is the Department of Defense, and the second is the National Telecommunication Authority, which is basically the entity that manages federal spectrum. So not commercial spectrum, but federal spectrum holdings. And the Department of Defense, pretty much think of it as a tactical environment. Every issue we've discussed is going to be looked at it. So I'm going to look at it through that lens, and then also talk about standards and 6G. Thank you very much. So next slide, please. Yeah, so that was what just basically credentials and a few different perspectives from multiple different places. Next slide, please. Okay, so this one, I think the main takeaway here is we've heard obviously people refer to 3GPP and the path that we're moving on from 5G to 6G. I think what I want to draw attention are to some practical realities, right? So today, the 5G networks that you have are based on release cycles that are about 24 months behind where current standardization efforts are. So you're working on release 19 today in standards, but the commercial network offerings today are release 16. Why does that matter to this audience, or why it should matter, is because the additional feature sets that are available are not going to be available in the networks of today. And the mobile network operators are not going to do that because they don't see a service revenue side. So that's just a practical consideration with respect to the work that you as a researcher are going to do and what kind of a real world impact it's going to have. You have to account for that level of delay because the gatekeepers at the end of the day are large MNOs and service providers. The other piece is to tie this into resilience is and reliability. I'll just use the words reliability, redundancy, resilience. For 5 nines uptime for a major mobile network operator, doing a back of the envelope math, it means it equates to about 5 minutes of downtime per year. There is almost, is that even a real, realistic bar that we should be setting from a 6G perspective? I don't know. I leave that as an open question. Maybe we can think about this at the panel level, what realistic expectations and requirements are specifically as we are talking about the journey to 6G, which is officially going to begin next year in 3GPP, March 10th and 11th, 2025 in Korea, where 3GPP embarks on 6G journey. Next slide, please. So yeah, Marty did a great job sort of explaining what the evolution is, and he went into the 3 usage scenarios. I think this is the IMT 2030 wheel, and again, just follow the timeline for a second here, right? So IMT 2030 works on a 10-year time horizon. The requirements that IMT, and this is a global requirement body, right? Every nation has representation here, and this is the community, this is the agency, the ITU, along this IMT 2030 roadmap, that's going to define the requirements for 6G. So what affects everybody in this room over the horizon of the next 10 to 20 years is being defined now. And within the next month, those requirements are going to be finalized. And officially, they're going to be handed over to 3GPP, which is going to start to execute developing basic fundamental technology, applied research, all of that good stuff's going to happen over the next 24-month period from 2025 to 2027 to meet these requirements that are coming here, right? So that's just in terms of the excitement for anybody who wants to look at 6G topic areas. You are going to see those requirements become available, become furnished, and within the standardization realm, this is going to go, just completely, really, really fast in the next 24-month cycle. Next slide, please. So this is kind of the level setting of where we're going with 6G, and what we have done up until now is we've seen, and this is kind of a summary slide, but the main takeaway here is that we have seen this journey from 4G to 5G with service-based architecture, softwareized, programmable, end-to-end application systems where each part of the network and each part of the protocol stack has been, you have the ability now to define that in a programmable manner. And this is kind of just a notional picture, but again, we heard some inference on open radio access networks, we heard inference of open interfaces, and this is something that is available to you as an academic, an industry member, or a government agency today when you talk about realization for 5G networks. Next slide, please. Okay, so when we look at and this is just a notional picture, and I liked, the slide that Marty had up on looking at this as a cross-layer approach. I think my frame of mind was pretty similar. And what I did is I divided that into some of the drivers from and the word that I'm using is future G, right? So this is primarily looking at not just the requirements that are already being defined and will be solidified in the December timeframe, but now when we actually do all the study items, work items, and talk to different application domains, what are the main drivers that we need to look at? So heterogeneous access, to me, that means we're looking at multiple radio waveforms, not just a 5G waveform, not just a 6G OFDM, but we're looking at Wi-Fi, we're looking at integration with NTN, we're looking at low power, and we're looking at Wi-Fi, right? So all of that needs to come together. And what are sort of the required kind of system elements that will need to be impacted if you're looking at providing that heterogeneous access? So service is going to be very key. And then you're going to have to look at the end-to-end system as to how do you integrate and bring these technologies back through a core network. It's a completely separate question whether the service-based architecture that we have for a 5G core will be extended into the 6G core, or will that look for a completely new 6G standalone architecture? If you talk to industry players, they want to, and again, I shouldn't just label it they, but there is this notion of moving similar to what we did with 5G, move into an NSA mode, which is the journey that we are on. It took a long time for operator community to move from non-standalone mode, which was coexistence of 4G and 5G, to completely standalone mode, and that journey continues today. So the reality is that we haven't really seen the true potential of 5G, but we are already talking about 6G definition. AI-enabled service delivery, resilience. So this is again creating time scales that are machine speed, right? So this is when the human is not in the loop, and again using the power of AI. Most of us are looking at what OpenAI, ChatGPT has done with generative AI, LLMs. That stuff will now get embedded. And we've heard some references to the AI RAN Alliance, which is very heavily looking at this topic area. So we'll hear a little bit more about that, and we can talk about it in the panel. Then we're also looking at open radio access networks, which allows network customization for each application domain, right? So Honda-san, and again, sorry to pick on you, but talking about disaster recovery would become an application domain area where we need, and again, borrowing a term that Marty just used, not a normal mode, right? So that's not a normal mode where we are not looking at high capacity video streaming, et cetera. We're looking at low energy bits for safety communication reasons. So how do we build a network that is customized to those needs? And I think that will only happen if you have a very clean slate approach, whether it's open interfaces, whether it's programmable APIs, and how do you sort of connect all of these disaggregated radio elements together to provide that service offering to meet the key performance metrics that we have defined for ourselves. It's almost clear now for 6G era, we heard about FR3, but there is no clean new spectrum that's available. Midband is a completely complicated and complex mess. There are multiple different incumbent partners, whether it be satellite, whether it be radio astronomy players, whether it be public safety. So there isn't necessarily going to be 500 megahertz of clean spectrum that 6G will have. So sharing native programmable waveform would be something that the 6G initial research is going to have to look at. And that's going to be very important for us to continue to focus on. And that obviously brings in the whole element of resilience, right? So everything that you see here is connected back to resilience and redundancy. And I really appreciated Warayama-san's framework in terms of defining how do we always sort of fall back on redundancy to solve our problems. And then last but not the least, security, encryption, and trustworthiness. So we need to be able to, we heard from Nagara-san that security is extremely important. For us, it's cross-layer, right? So you have to look at device security, you have to look at software bill of material security, and what are you going to allow? In the US, we have this notion of a zero trust architecture. It is something that we are trying to bring to the standards, which is basically you don't trust anything. So now, given that paradigm, how do you design solutions? How do you optimize? And what do you keep secure versus what do you not keep secure? So what's the opportunity cost of security? Should we care about it from top to bottom, right? That's again, an open question. Next slide, please. So all of those were sort of some of the key drivers. And then what are the enabling technologies that, we feel we're going to need to look at? So starting from like a high level application side, the idea of, mixing together the cloud, which we've seen forward integrate. So we've seen the cloud move, basically consume the entire core network. So majority of your MNOs are working on cloud operated core networks. We've seen the cloud move all the way into the edge. And I think we're going to see a continuum where communication, compute are basically going to be omnipresent. So it will be availability of compute where it's needed and when it's needed. And the communication compute paradigm is going to have to be, define new kind of hardware architectures. At the end-to-end system level, we're seeing AI ML. Again, no need to get into that a lot more. I think the other piece I want to highlight is the slicing and RAN sharing, right? So neutral host infrastructure. Again, we don't want dedicated infrastructure for each application. So how do we sort of build neutral infrastructure, especially as the spectrum becomes more complicated? As MNOs have to support multiple bands, each band can't have its own radio unit antenna mast mounted. We have to get smarter. We need hardware innovation. We need device innovation to support multiple bands. We need more efficient power amplifiers, LNAs, the whole chain of the RF front end, the ADCs, the DACs. We need to rethink how do we do that in a more efficient fashion to support multi-band radio operation. And then on the mobile system itself, we need technologies that allows infrastructure-less communication, specifically in disaster resilience waveforms when the infrastructure is not available. So side-link communication is something that's extremely important. MANA networks, how do you self-form? How do we sort of do this at a network layer, leveraging, routing protocols, et cetera? And then, further down, how do we do more two-side link, for example, which is we need communication direct device to device without the infrastructure being available. Next slide, please. Okay, so this is just a, kind of a whole amalgam of the things that I talked about. I think the only thing that I wanted to mention here is the notion of sensing. So what is now exciting is this ISAC concept, JCAS concept, whatever you want to call it, but the notion of a G-Node B being a radar for that matter, right? So now you're able to leverage what we call in the sensing world, signals of opportunity. And how do you use that for sensing on the same channel that you're able to do the communication on? And then this is obviously has huge implications on indoor personal area networks for localization, for tracking, and for activity recognition. And then last but not the least, these hybrid network integration and resilient waveforms. So how do you operate when the noise levels are high? We heard an excellent talk earlier about electromagnetic interference at the hardware component level. That culminates, and that also has direct impact on communication. So how do you build these waveforms that are more resilient? OFDM can't be the answer to everything. So we have to be very careful on how do we design these things for 6G. And I'm sorry if my tone is a little darker, because it is something that we have to, really come together, because it's not just about pushing more bits. Here, we have to be very strategic when we're thinking about resilient systems in the future. And I think there is a lot of work that needs to be done. Next slide, please. So this is just one effort that the US Department of Defense through the Chips and Science Act, and I think it's important to highlight it here because this is a journey that we're about to embark on, which is this initiative called OKUDU, which is the open source CUDU. And what this is it's going to provide a completely open source implementation of the software, which would be an Open RAN compliant, 3GPP compliant base software that would be available to the broader community. So this obviously benefits the US government, benefits the Defense Department, but also as an academic and an allied nation, you have the ability, because this will be put out into the open source domain. The piece that's more interesting is the hardware side, where we're also building hardware and the abstractions or co-design between software and hardware as to how do we, you're looking today at CPUs, GPUs, and FPGAs, and all of that supports your distributed unit, your central unit, and in some cases, majority of your digital design for your RF front end as well. So how do you program that stuff without knowing? Not everybody's a CUDA expert, not everybody's a DSP expert. Not everybody is an x86 architecture expert. So how do we build the abstractions that allow us to build these accelerated, performance and highly reliable systems? And we believe, or at least on behalf of the Defense Department, we believe that open source is the answer, and high performance architectures and abstraction layer is the answer for this. So happy to get into more over the panel. Thank you again for your time. Thank you.
Thank you very much, Mr. Manu. Now, if I can call for Professor Tommaso from William Lincoln Smith, Professor of Electrical and Computer Engineering and Director of the Institute for the Wireless Internet of Things at Northeastern University, to speak on Open 6G, enabling an AI-powered society through open, programmable, and intelligent networks. And I think while we're waiting for the screen to share, I think it was particularly interesting, the point of not trusting anyone as a new sort of perspective on resiliency as well. That's not a concept I think that has come up in the different presentations regarding resiliency. So hopefully we can hear more about that in the panel discussion.
All right, sorry for the technical glitch, and good afternoon, everyone. Great pleasure to be here. Today I'm going to talk a little bit about our work at Northeastern related to Open 6G. I'm a professor of electrical and computer engineering at Northeastern. I direct the Institute for the Wireless Internet of Things that is bringing together all the expertise of the university in the areas of 5G, beyond 5G, 6G, and systems at the intersection between the physical world and the digital world. All right, so a little bit about our institute. We are looking at, as I said, being an innovative force for research in the area of smart and connected systems. We're also an educational nexus. We're bringing together folks with expertise in the classical world of communications and the world of networking and computing, as well as algorithmic development, with a focus on hands-on and experimental research. We're a think tank in the sense that we participate in a number of events that contribute to shaping the global discourse on the future of connectivity. And we are also a technology incubator. We work a lot with our partners in developing open source software and IP in the space of connectivity. Open 6G, as I mentioned, is industry, university, government, cooperative research and development center that is looking at developing the next generation of systems based on the principles of openness, programmability, and algorithmic control. We are developing architectures for the future of open and programmable 6G systems, open source software stacks. We're working very close with the Open Air Interface Software Alliance in developing that. We're working on creating a family, an ecosystem of programmable testbeds to enable experimentation in this field. And we work quite extensively on algorithmic control based on artificial intelligence and machine learning, as well as on automation techniques based on modern CI, CD, CT techniques to solve problems in the areas of security, spectrum sharing, and energy efficiency in this field. So what are some of the problems that we are addressing with Open 6G? The current networks are not resilient in many ways. They are not programmable, and they're based on monolithic infrastructure, right? You buy a base station today, it's very hard to update, improve, or reconfigure unless you are working closely with one of the few vendors worldwide that are able to do that. This leads to vendor lock-in. All the technology in a certain area for a certain operator is based on the same vendor, and it leads to limited competition and a supply chain that is not resilient in many ways. It's very hard today to programmatically control networks, to programmatically observe. If you need to reconfigure a network because something is not working the way it's supposed to be, you need to send a team of engineers, right? And ideally, would like to be able to automatically have the resilience inherent in the system to provide, to be able to reconfigure the network. We have a lot of manual configuration, as I mentioned, and there is a growing and significant gap between theory and practice of networks. We know a lot in theory, especially in the academic community, about how to optimize the behavior of network, how to make them more resilient, but we cannot do that in real systems. And this leads overall to systems that are not as resilient as we would like them to be. Single vendors, exclusive spectrum access without the ability to reconfigure spectrum access in real time, limited flexibility and adaptability, and complex and expensive update cycles. Now, I promise you it's the last time that you see this figure today, but the promise for 5G and beyond is to be able to support diverse and heterogeneous use cases. And for that, we need flexible and programmable architectures. And also, the complexity of the networks going beyond 5G is increasing significantly. We've heard about this in many of the talks today, right? We have a diversity of devices trying to support different use cases, sensing, mobile broadband, control, etc. We have a diversity in spectrum. 5G introduced millimeter wave. 6G is likely to introduce FR3. We heard about it in the previous talks, 6 to 24 gigahertz, somewhere in that area. But it's also possibly, maybe in 6G advanced, going to introduce terahertz communications. There is a significant diversity in protocol stacks, certainly coexistence between wireless and wired, but also integration with non-terrestrial networks, etc. And all of integrated access and backhaul, I think this will also be an important topic, very much related to the resilience that we're talking about today. So we need to have network architectures that will help us have the flexibility to introduce automation and intelligence so that we can manage all of this complexity in the network in an automated way without having to configure millions of parameters to get all of these complex systems to work together. Okay? So a big evolution that is happening with work that has been happening within the Oran Alliance in the last few years that we've contributed significantly at Northeastern is this evolution towards open, programmable, and virtualized wireless systems where all the functionalities that were traditionally handled in the base station sitting on a tower, right, are migrating to a set of disaggregated entities that are executed in a virtualized environment on the cloud, specifically the distributed unit and the centralized unit. These are also connected with open fronthaul standardized interfaces to radio units that are becoming basically software radios, right? Radios that are directly controlled through IQ samples in the frequency or time domain, depending on different splits. And also the other big thing that is happening is the introduction of something that is referred to as the RAN intelligent controller, right? RAN intelligent controller is an abstraction of the network functionality. It's a centralized abstraction that enables observability on this distributed, disaggregated, virtualized infrastructure. So you can see at different layers of the protocol stack what's the status of the network in a central point. And then it enables injecting control actions based on these parameters that you can observe in real time or in near real time or on longer time scales. Okay, so through this combination between disaggregation, programmability, and RAN intelligent controllers, the network is becoming more open and becomes amenable to control by means of artificial intelligence. AI will likely transform cellular systems as we conceive them today, will enable a number of different applications that will increase the reliability, resilience, and security of our network, while also creating a more flexible infrastructure. We're going to be able to classify by observing the network through these open architectures, different traffic profiles, understand anomalies, outages, and various mobility patterns. We're going to be able to forecast right? Predict a much more fine-grained way what is happening in our network in terms of traffic loads, mobility, the need for handovers, etc. And we're going to be able to control the behavior of the network in an automated way, right? We're going to be able to restore functionalities that may have been attacked or may have failed, right? So there's containers that are providing G Node B functionalities, DU, CU. If they fail, we can restore them in an automated way. And similarly for core functionalities, right? We're going to be able to slice the network and provide differentiated resilience and differentiated security in different ways. Load balance, provide adaptation in resilience, for resilience, and many more functionalities. So all of these things, I'm using the future tense because they're not part of production networks. But these are things that are happening in research labs today in our group at Northeastern. We've been looking at a number of different functionalities. And we've sort of classified different control loops that can provide in the open radio access network between, in the interaction between what you can observe and what you can control, different functionalities. So at different time scales and looking at different levels of input data. So we have different forms of control applications that interact with the control plane of the network and provide automated closed loop control of various functionalities. Through our apps that operate at a non-real-time scale, we can control, we can inject policies in the network that provide, you know, that inform the network what to do in case of specific events, right? And how to react to the specific events. XApps operate on a near real-time time scale between tens of milliseconds and 1 second, and can control functionalities like load balancing, handover, selection of different scheduling policies, how to slice the radio access network, etc. And then there's something called DApps that have been promoted and introduced by our team at Northeastern. DApps extend the ORAN architecture in 2 different ways. One in the domain of authentic real-time control, functionalities that require closed loop control in less than tens of milliseconds, right? Think of a few milliseconds, microseconds, etc. So authentic real-time. Also, interaction between the user plane and the control plane. That's something that we can do with the apps that you cannot do with classical XApps and our apps. The apps run directly on the distributed unit or in the control unit, or potentially also the radio unit. The apps have been proposed in the ORAN Next Generation Research Group. They've been an approved study item, and we're hoping they received a lot of support from industry, including companies like NVIDIA, Mavenir, and others. And we're hoping that this will become part of the real architecture of 6G. Another thing that you can do with the apps is, we talked about this quite a bit, integrated sensing and communications. This is an example of the apps running on the G Node B that provide direct classification of the spectrum of what is being observed in the spectrum. So you have a G Node B that is looking at what's happening on the spectrum and classifying in real time what transmissions are happening on what frequency bands, including Wi-Fi, LTE, Zigbee, etc. All right, this is pretty much what I wanted to cover today. I just wanted to add one last comment. Resilience is also about creating secure networks. When we go in the direction of open, programmable, and virtualized systems with this disaggregated architecture, we need to secure this infrastructure. And securing this infrastructure means securing the open interfaces. By introducing these open interfaces, we are, in a sense, expanding the attack surface, and we need to make sure that these interfaces are secured. And there's a lot of research activities happening in this space. We need to secure the infrastructure, the cloud and virtualization infrastructure that is supporting all of this network needs to be secured. And also we need to secure the intelligence, the closed control loops that we mentioned, we need to make sure that the data that is used to train the models is not poisoned. And if the data is poisoned for whatever way, we have mechanisms, algorithmic mechanisms in the system that reduce the effect of data poisoning attacks. And that's what I wanted to cover, and I'm happy to discuss it more detail during the panel.
Thank you, Professor Tommaso. I'd like to next call for Professor Tomoaki Otsuki from the Department of Information and Computer Science, Faculty of Science and Technology, Keio University, to speak on research on sensing, actuation, communication, and intelligent signal processing infrastructure for smart environments. So we are a little bit pressed for time, so if I could ask you to mind your presentation time as well. The floor is yours.
Okay, thank you very much. So I'm Tomoaki Otsuki from Keio University, Japan. So I'm very glad to be here. So already introduced, I'm one of the PI of the another Aspire program. So we are working on, the title is a bit long, but we try to realize the ambient intelligence. So I will introduce later, but ambient intelligence is a very broad but important concept, also that related to this, I mean, a panel or talk, or even a previous panel. So first, yeah, I want to introduce our members. So in our Aspire program, so we have many members from the US, University of Houston, UC Davis, also Canada, Norway, also the UK, and also also the Australia. So we are working on, as I said, ambient intelligence. First, I want to introduce the concept of ambient intelligence. So as the name mentions, ambient intelligence is the environment. Environment itself has intelligence. So that try to support people. Yeah. In order to do that, of course, the sensing is important, and also the sensing information we need to collect, and also that we analyze the collected data, and then take the good, reason or reasoning, and then based on it, we also activate the environment. So then for kind of the closed loop, so we want to establish. So today, because various topics we are working on due to the time limitation, I wanna pick up some related to resilience. Yeah, I will. So not the same slide, 6G. And because here is Japan, so I pick up this one from the NTT Docomo's white paper. Okay, so already, so some speakers mentioned, even compared with 5G, I don't know, pointer? Maybe no pointer. Yeah, we have the various kind of, in various aspects, we need to improve the performance. So of course, the high data rate, very important, and also the extreme coverage extension, low energy cost, and also latency, and reliability, also the very closely related to today's talk, and also the massive connectivity and sensing. But not only this, already some speakers mentioned resilience or robustness, and also the security or secure is very important. So unfortunately, so I couldn't see the yesterday's talks. Then maybe you have already shared the information about the earthquake in Noto. So unfortunately, we had a big earthquake in Noto Peninsula in this January 1st this year. The magnitude so very large. So you can see the map, Japan map over there, and unfortunately, huge damage to that area. And then, so how about the damage to cellular networks? Maybe a bit hard to see, but left side, you can see some base station collapsed one. And also the damage to the optical fiber, and also the damage to the buildings, or some, communication equipment installed. That means we have a big damage to only the wired and wireless communication. So these figures show the cellular network service disruption areas in several major telephone companies, cellular communication companies like NTT Docomo, KDDI, and so on. So just a few days after the earthquake, so you can see the service disruption area in Noto Peninsula area. Like for example, NTT Docomo, 70%. And also the KDDI 54 and some others. And so the wireless communication or cellular communication are kind of the social infrastructure. Without this, yeah, it's very hard to live, or even the younger generation cannot survive or cannot live, right? So very important, like a kind of the lifeline. So we need to, yeah, make it robust, or we need to recover very soon. But so this is the number of base station outages, I mean, due to the earthquake over about 2 months. The first one, left side, Japan, January 1st, just the same day earthquake occurred. And then a lot of base station outages we had. Even after 2 months, so still some uh, outages we can see. That means we need something. We need to make it robust. We need to make it recover soon. And also this figure shows the cause of outages. Now, of course, the power is very important. So power outage in total about 70%. This is the reason. And also the line break, like a telephone line, optical fiber line, and also the around 60%. Those, of course, very important. Also, we need to consider. So these are the emergency recovery equipment that are already installed or prepared. So there are several like for example, the satellite entrance line. Satellite is very important. I will talk about it later. And also the power, very important. And also the base station, already mentioned, I mentioned many base stations collapsed due to earthquake. So around you remember the Fukushima, right? So Great East Japan earthquake. That is the 2011. At that time, we had only these, but still, yeah, some okay, but not enough. And then this year, March, we had it increase, but still not enough. Then, how much we used for the Noto Peninsula earthquake period? Only this. That's not enough. Also, we need, yeah, of course, there is a trade-off, how much we, yeah, spend for this kind of the preparation. But unfortunately, we Japan, we have a lot of natural disasters. Yeah, of course, we Japanese know. So typhoon, earthquake, and so on. Yeah, many international students, yeah, in my lab. So they come and first experience earthquake, they scared. But yeah, soon they got used to it. We have many earthquakes, right? But we need to prepare. And also during that period, LEO, that is the low Earth orbit, so plays a big role. Not, I cannot say not for, I mean, customers, but for people who went to the place to recover the, I mean, system. So they mentioned, so the Starlink is, yeah, very helpful. Maybe some of you are coming from a different field, but you can see what is Starlink, this one. We are, I don't know, a bit worried about this one, but anyway. And one of the topics we are working on for the resilience is the hubs. Hubs is a high altitude platform station, like this kind of the kind of a large UAV or unmanned aircraft. Right now, once launched, then about 64 days flying over the air. Then how we use it? Also the how or why hubs is important. So this is a figure where hubs is flying or will fly. You can see, so hubs, the name is a high altitude platform system, but the altitude is just around 20 kilometers. And maybe a bit hard to see, but around that, altitude, we can expect a stable airflow throughout the year. That's also very important because this is the unmanned one, right? Leo, like starting, it's okay. Compared with Geo, much closer to the Earth, but still, yeah, you can see around 2,000 kilometers high, right? Sometimes okay, but hubs many advantages. Of course, yeah, everything has pros and cons. But yeah, some advantages of hubs over the other system is like this one. One is, well, we can still expect a wide coverage compared with particularly the terrestrial base station. That's important in emergency scenario. And also the big thing is latency. Latency, because very close to the Earth. Then, as you can see, round trip propagation delay, yeah, this is just a service link only, but still much shorter. Yeah, of course, compared with Geo, much small. And also even compared with Leo, much small. So some application, Leo is okay. I don't know, some of it, or online, maybe someone from KDDI. So yeah, Leo is okay. Yeah, they are providing the service for the Starlink, but apps has some advantages over it. And also the very important thing is our primary objective. One of the primary objective is, as I mentioned over there, disaster prevention. So it is easy to deploy. Of course, well, no, or they are close to the no effects by the earthquake. Then something happens, still, yeah, we can deploy quickly and we can provide a service. That's why hubs is very important. So the research and also the, yeah, even the service or business, so the hubs, about the hubs. Japan is very fast. So then we are expecting 1.5 years later or 2 years, we try to start service. So two companies now, they are talking about the implementation of this kind of system in Japan. And also the various kind of the application we can expect like this. Yeah, of course, over there, disaster management and also the related to this laboratory Earth observation and also. And then, as I said, this is very important idea. Not a single system can be helpful. Resilience should be based on the multiple or integrated system, right? So in terms of the space or air, so surging or saging or we call space air ground integrated network. That's a very important for the resilience. Yeah, there are many phases in resilience. So some speakers already mentioned geo, rail, hubs, and also even the terrestrial base station for a network. We should combine and design the network together. So this is a very important idea. So we are working on, of course, also the in Aspire project, and also the each link so has different characteristics, latency, capacity, also the budget, like a power, also quite different. Then considering this, considering the content requirement, how to route the data, particularly in emergency situation, also even the daily life, that's very important. That's also the very important research topics in this field. And also this one, so related to the previous panel, I put it because we are working on also we developed or theoretically the very, low energy consumption sensor. So the receiving the communication signal based on it, yeah, of course we detect or receive the sensitive information, but also we use the power, receive the signal power to, drive. this kind of sensor. So I don't go into detail, but this kind of technique also important for resilience. Okay, in summary, so wired, wireless communication, already the social infrastructure, probably they are always agree, and robust and resilient, very important. So I just introduced the two, staging and also the high accuracy integrated sensing and communication, but other technique also very important. So maybe during the panel, we will talk about it. Yeah, that's the end of my talk. Thank you very much.
Thank you very much, Professor Otsuki. And now we would like to invite Professor Akihiro Nakao regarding his presentation on inclusive creation of next generation cyber infrastructure.
Okay, so we have a big problem about timing. So we are one session late, so we have to be a little bit quick, but I have to give 5 minutes to Mia because she is speaking about his experience as for spending her time in Ulu. So let me talk about my Aspire project. The title is Inclusive Creation of Next Generation Cyber Infrastructure. An Aspire project, the main objective is to work with the foreign institutions and on a specific topic. And I'd like to introduce all these institutions. So at the top, we have Ulu University. I'm glad to see that Matti is back in operation. He recovered from his absence, in our event. And also Power and Northeastern, they're representative from there. So we are working with all these institutions, but our project, so this is about strategy. So we like to establish fundamental technologies for next generation cyber infrastructure, even more robust as a social infrastructure. And we would like to promote local 6G because, so in a minute, I can talk about what the local 6G is, but we need to develop a strategy because when we talk about resilient infrastructure, telcos may not have good incentives to develop that because they can't make, or monetize that from robust and resilient infrastructure. I mean, what they have to do it by design, as Matti said, but putting lots of money into this resilient, robust infrastructure, maybe you can't justify the ROI because you have to invest a whole lot of money. So we have to borrow and we have to borrow the power of the people. And I like to advocate that we need something like a local 5G. So the local 5G, you can deploy your own base station and you can deploy your own 5G wherever that is needed. And also you can develop your own, the base station like this. So I'm skipping this because I have explained this in the past days. We can develop our own SDR card and we can, build your own base station and use that for the local government revitalization and all that. And we are using that in Mount Fuji also. But so there are lots of interest in that, So mostly, so people are interested in a business using the local 5G base station. And this is a good thing. But when it comes to resilience, we have to think closely about a strategy. So we are evolving 5G system into 6G, but we have a local 5G, which we can use to bring innovation locally. And we can do lots of customization, and we can do ultra low power, LEO local 5G integration, application slicing, all that. AI run, many people today talked about that. We can integrate AI into radio access network. But at the same time, we can develop solution that telco cannot come up with. We can, integrate AI to make a system resilient. So we have to democratize the system to make resilient mobile network infrastructure. So this is a strategic proposal that I have in this Aspire project. So let me introduce what we do with this, the local 6G base station system, and not necessarily using this base station system itself, but by imagination, we can develop ideas on top of that. What if we can modify the base station to integrate the new ideas? Okay, so this is the work done by my students. So he's trying to use multiple operator networks at the same time to make the mobile communication system very robust. If you use 3 mobile networks carriers at the same time and switching between them, we can make it robust. This is done by my bachelor student. And if you look at our poster, you can learn more about it. And I'm not going to explain that. And also, so this is network slicing, but so there is no index to measure how good isolation is in network slicing systems. So he's also trying to develop the index of how well that we can do isolation in a system. Okay, and another thing is that so this bachelor student is trying to build a congestion control over millimeter wave communication. So the millimeter wave communication is well known to be very hard to use because high frequency band it's not easy to use. But he is trying to use that and trying to make the millimeter wave communication to the limit. And for that, he needs to develop the congestion control system. And yesterday, I talked about this application, and we are working with MFRI to make a robust local 5G system with help with Starlink. But the Starlink communication, people talk about it, but it's not stable at all. It breaks, from time to time. And if you look at the throughput, so then it fluctuates every 15 seconds. And you cannot build the stable system. So my student is now working on a congestion control system on top of this very fluctuating, mobile, the satellite system. So all these ideas, students are developing these ideas because they know that we can customize the mobile network system. So this thinking is very important strategically because we can democratize the system and borrow the ideas from even students can make the system robust. Okay. And another thing that we are doing with Rakuten is that, build a mobile system. You can use regular user equipment and unmodified user equipment can talk to the giant satellite. It's a LEO, but for this, you don't have to have the latest iPhone system to talk to the satellite. We can use a regular phone or even IoT sensor that can talk to LEO satellite because it's a giant antenna. So you can take the very small power from the UE and make communication available. So I can't talk about a detail, but we published this paper at Globecom. We're going to go to Cape Town to present the idea. And then now we submitted one paper with Rakuten and the first field trial. And in fact, I can tell you that the communication was successful and we can report that later. Okay. So one last thing that, AI RAN Alliance, and I'm skipping all these because maybe in the panel we can, dive into the detail. Northeast and New Tokyo join AI RAN Alliance to use AI into the system. But I like to point out that, we are now evaluating the potential application of LLM in a system to make mobile system robust. So we try to get the log of the mobile system and feed it to LLM. And at the same time, we can feed the program of the open source base station program into LLM and tell LLM, optimize it, right? And it's not really optimizing it, but it can point out what is wrong in a code. And we like to use that for continuous integration of the development of the mobile system. So this is something that we can do. And this idea comes from our democratization approach. Okay, I'm skipping all these. And we can talk about this in the panel. I can share my slides later, but we like to make strategy of democratization. Everyone inclusively can attack the problem of the resilient mobile system. Thank you very much for your attention. And I'm now switching my microphone passing my microphone to Mia.
All right, thank you very much, Professor Nakao, for your presentation. So I'm going to be doing a presentation on some of my experience abroad regarding my study abroad at Oulu University and some of the standardization activities that I've been involved in. And it's sort of an emphasis on why students should consider studying abroad. So we could go to the next slide and then move on to the next slide right after, actually. So I'm just going to highlight some of the experience that I've had. From May 2022, I started doing an internship at the International Telecommunication Union, which was actually an internship introduced to me by Professor Neko. I was part of the AI and 5G Challenge as well as the AI for Good team, and I worked there until February of 2023. Next slide, please. And as of July of 2023, I have been working at Nakao Research Laboratory as well. I support with the various ITUT related activities, especially the AI and 5G Challenge, and I've attended some of the conferences and meetings abroad. This year, I went to IIT Hyderabad with the Sharp Semiconductor Innovation Corporation to discuss some of the collaboration points between India and Japan. Next slide, please. And I'm also working for an SDO in Japan called Telecommunication Technology Committee, and I've attended various study group meetings, TSAG meetings, and recently I attended WTSA, which is an assembly that happens once every 4 years to decide the next study period for ITUT. Some of the most interesting things and the two key takeaways that I have from here is that A, there is a new resolution for AI, which is a big step. And there's also a resolution for next generation experts for standardization human resources, which is incredibly important because there is a lack of young experts in this sector. I was also a moderator for a panel at one of the side events regarding next generation networks. The panel discussion was made up of professors, researchers, and startups between India and the UK. And the interesting points for here was that there are a lot of specific verticals that had yet to be identified where 5G and 6G solutions could make big improvements. The other key takeaway is that collaboration via campus DevSpeds, although it's already starting, it should be explored even more. And this was one of the key takeaways from the panel discussion. Next slide, please. And currently, I'm a first-year student at Oulu University, majoring in wireless communications engineering, especially radio access networks. And these are just some of the things that I've learned across the last few months. First is that there is a big emphasis on a global perspective. And I've put up there, and it was quite interesting to see the other presentations today, because there are many mentions of standardizations, especially the IMT 2030 from ITUR as well. And there are also a lot of specific standards that I mentioned in more detail during some of the other classes. And that's something that I've found to be quite different in my experience abroad. There's a lot of career support as well, as career support during the master's degree program to gain more hands-on experience, and career support for post-graduation as well. And there's also quite a big collaboration between industry, academia, and sometimes even government as well. So I often feel Nokia's presence, and I think this relates to the scale of research as well. I had the pleasure of visiting one of the anechoic chambers at Oulu University last week, and I was extremely surprised by its size. And so I think this all leads to something that is the point of my presentation today. It goes into the question of why study abroad. Well, one of the main things that I garnered from my experience abroad is that I gained a very big difference in perspective. My apologies. In terms of the discussions held at APT and the discussions I've seen at ITUT, especially regarding the resolution on AI, different countries had many different opinions, and discussions I saw at APT, the Asia Pacific Telecommunity, were very different from the discussions I saw at ITUT. The use cases that SSIC in Japan had in mind were very different from the use cases that India IT Hyderabad had in mind. And the perception of standardization, the perception of how important standards are, also differ depending on country to country. Telecommunication, especially the solutions that come out from there, will not only be applied locally but globally, as we've seen. And so the idea of knowing how different people will perceive those situations, how they'll be implemented differently, is, I think, incredibly important. It's incredibly important to understand how they come about, especially when starting research. And it's definitely why I recommend that students, researchers, have a lot more experience abroad. And I think it also leads into a bit of international collaboration as well, the importance of it. If we go to the next slide, and then one after, actually, right after. Just in the few months that I've been there, I've seen a lot of collaboration between Finland and Japan that I think is incredibly important to highlight. Just last week, there was a joint 6G workshop between NICT and University of Oulu. And even on a different scale, we had high school students from a Japanese high school come visit to see how some of them might be interested in doing an exchange at Oulu University as well. So hopefully this brief presentation highlights just how important I believe that international collaboration is on terms of academia, but in terms of a more upper scale international collaboration as well. Thank you very much.
Thank you. So maybe we should go directly into the panel because we don't have time.
Yes, that's
So,
exactly, yeah. So if I could invite everyone up to the stage here, please. And I will pass on directly to Professor Nakao to moderate this session.
okay, Matti, are you with us?
Yes, I'm here.
Okay, okay, good. Good to see you. Let's see. Let me pull up my slides. So thank you very much for joining this panel. And some of you must take a train back to Tokyo. So we cancel the break and we are now going into the detail of the panel discussion. So let me share this slide. Okay, so I already gave these 3 questions to the panel, but let me briefly recap what the people said today. And Matti talked about, I actually see that Matti gave an answer to all these 3 questions, but he stressed that, so he liked to push resilience by design. And the 3GPP should consider seriously about this resilience, in the mobile network architecture. And also, Manu and Tommaso stressed that we should have a programmable infrastructure so that we can adaptively, resolve the new problems. And Tommaso also mentioned that we should have an open 6G infrastructure. And I said that democratized approach is good. And Otsuki sensei mentioned that he already have a space air integrated network and also sensing integration. So these things, we all talk about it is, resilience and a different, approach, but I think we have the same objective. So, okay, let's attack the first question. What constitutes the resilience in telecom infrastructure? So I think a resilience is, people define in a different way. So what is resilience in your project, in your opinion, so Tommaso.
I'll start. For us, resilience is the ability to create an infrastructure that can reactively provide connectivity in case of faults and in case of attacks. And so this is the main two aspects. And you know, in our vision, really it's a combination of openness and the ability to create a communication infrastructure that relies on a generic compute infrastructure and connectivity with radios, right? If we can elastically and flexibly reinstantiate our communication software on different computing platforms, right? And connect these different computing platforms, instantiating the communication infrastructure reactively to radios that can provide the physical connectivity. That's how we can create a resilient infrastructure. So this needs a combination between a new approach where you combine these virtualized workloads on a generic computing infrastructure and algorithmic control of the network.
Maybe can I say something?
Okay, go ahead. Yeah, sure.
So, so I do agree with Tommaso that this is definitely the right long-term goal. But there are a bunch of things that we can do in relatively short term. Just to give you one example, this making 911 calls has been standardized. And there, the approach is that in that event, national roaming is forced. How about forcing national roaming in some other situations, some emergency situations, whatever those are? And that type of things are very easy to, it's a regulative decision and governmental decision to force operators to collaborate more. And there is actually, I don't remember the name of that, but not many years old effort in the US that was made to little bit, it was not forcing, but to initiate discussion in the USA, how operators could collaborate more. Maybe you guys are familiar with that, but that's the first step to do. And then let's make the next steps in action.
Yeah, so Marty, one was NG 911, next generation 911. Your point about national roaming, I think sometimes it's forced on you. So in the case of Ukraine, when Ukraine knew that Russia was going to attack, the first thing for communication infrastructure that was done is national roaming was instituted. It wasn't prevalent. Multiple MNOs within Ukraine had their own networks because of resiliency, because they knew that there would be attacks, obviously, to the infrastructure, but also they would be doing it online, right? So they would be spoofing you, they would be doing denial of service, DDoS attacks on your infrastructure. So national roaming was done. Now, obviously, not every country is going to be have war as the primary reason to institute national roaming, but that was something that was done successfully. And to this day, Ukraine has been able to maintain. So it is a shining example. Unfortunately, circumstances are not key. NG 911 was something that was forced by the U.S. government, but I think it was a very lightweight approach. It got severe pushback from the MNOs, which is a very powerful lobby in the U.S. Congress. So that was basically stifled. From an innovation perspective, there were key innovations in how the IMS systems could be developed, how you could have multiple operators, mandated to provide that level of infrastructure. What the US government ended up doing is we ended up creating a separate physical infrastructure called FirstNet. And that is done primarily not for common citizens, but it is primarily available to public safety officials. So it's a dedicated infrastructure that's operated by AT&T today in the US, completely separate, where AT&T provides a portion of dedicated spectrum and communication infrastructure primarily for public safety purposes and reasons. So whenever we get hurricanes, natural disasters, or emergency situations, it's that network that has been used. But it's a policy failure in my perspective. It should not be done. You wouldn't need to have a separate physical infrastructure, but unfortunately, that's where we are today.
Okay. So the Mati's message is that there is a long-term goal, maybe Tommaso was mentioning, and also we have to have a short-term goal, and that there's something we could do, like the energy 911. By the way,
can I make a very quick comment to continue?
Go ahead.
So operators are the key, of course, obviously, like Manu was explaining. But let me give an example why they are just working to different direction in terms of resilience. Battery backups are really key in survival of base stations in power outages. And currently, today, site sharing between multiple operators is really practical way of them sharing infrastructure costs. And when they're doing site sharing, they're sharing also the battery backup. So they are actually going to exactly opposite direction in terms of resilience. So lots of practical things could be done in really short term to improve resilience of networks. There are lots of different things that could be done.
Okay, so site sharing, and also I do have opinion about that. The site sharing for battery backup, and also national roaming. So Japan actually talked about this because KDDI had a very big disruption last year. And then government took it very seriously, and there's a movement of something like Energy 911. But it's very, I mean, this leads to what Matti mentioned. So if we introduce some complex system of national roaming, so if something breaks, that may break other things too. So we have to be bit careful, and I'm glad to hear that US has successfully did this already. Okay, so Otsuki Sensei, do you have any opinion about the resilience? What means resilience? What the resilience means in telecom infrastructure?
Okay, so yeah, already mentioned, so there's some important, but resilience, there are many phases. So some speakers mentioned as in some sense, recovery and also the robustness, also the very important. So not a single system integration, and yeah, it's related to international collaboration, also the related to standardization, particularly yeah, emergency call, even frequency itself is also important, and also the space terrestrial frequency allocation and over some countries. So then, yeah, in short, robustness or quick recovery was important, and also the robustness already, yeah, talked in the panel in the previous one. So theoretical aspect or theoretical approach is very important. So not only, yeah, of course, standardization, but it should be based on some theoretical approach should be. So we are also working on those kind of theoretical approach.
So, okay, so I do have a question for all these panelists. So we know that we need to do resilient infrastructure, but who forces that, right? So the telcos seeking for profit, for example, right? So it's very hard for them to invest on the resilience. And as Matti said, that they moved from private 5G to completely public 5G for emergency operation, in his slide, right? So who can force the resilient mobile infrastructure? Of course, government can, right? And maybe standardization can.
So, so standardization, I have a more kind of pessimistic view, because if you look at standardization, release work items, etc., resilience is covered. The stifling piece is this word called optionality. Optionality meaning in standards, work is defined, but a vendor will never, excuse me, vendor's never going to implement that feature. Why? Because there is no requirement, there is no demand driver, there is no pull. The economy, right? And then there was, I think somebody had this point, maybe Marty, you had it on your slide, which was, what if we do nothing, right? So resilience, let's forget it. Let's do nothing. What is the cost, right? It's simple economics. If there is a event, and the slides you put up for Norso, you showed so much devastation and destruction, but the opportunity cost of investing in resilient infrastructure versus basically building the tower again, basically putting that optical fiber cable again, right? So that kind of a cost benefit analysis, I feel, the MNOs have done that, and I feel unfortunately they're falling on the side where doing things over and over again is probably more cost effective. And the other thing is, when you're not making additional revenue, right? Is it a marketable thing? Will people here pay an additional $1 a month if you say that I have a more resilient network? I don't know. Not, maybe an enterprise private network may, because they have requirements of 3 nines, 5 nines, industrial robots, power failure, like they need that stuff. But for an average common person, so the economics is my angle, and the issue is it's not a study item or a theoretical thing. I respectfully disagree, because those study items, work items, are part of release cycles. It's just that the optionality of that network, or how those study items are accepted into the standard, they're not part of what the operators ask the vendors, and that's not part of what the vendors offer to the operator. So we're stuck in this kind of a loop.
Yeah,
But
it's
I
always
think
good
that
to have.
the key challenge is that the regional differences are really huge. Situation in the USA is very different from what it is in Japan or, for example, Finland. So for that reason, I would say that there should be flexibility, and standards should enable it, flexibility to have national approaches depending on the national needs. And if the standardization is not paying any attention to improve resilience, whatever ways in technical terms they are going to take, if they're doing nothing will ever happen, of course not. But the needs will not disappear anywhere.
Yeah.
And if the 3GPP standardization is not going to pay attention, then it might mean that, well, these public authorities, private networks must be there in the future as well.
I think we can all agree probably that 3GPP, I mean, in general, the standardization bodies need to create the conditions and the frameworks for resilience. And then there needs to be some intervention from the governments through policy to sort of make sure that there are the right conditions to really make resilience a reality, right? Beyond all the speculation that we can have here. And this can be with a combination of creating economic incentives and just regulation.
Yeah, so we all happen to be academic. So is there any role that we can play from academia? So Tommaso and Manu mentioned that programmable infrastructure, and we can show that the value of it on top of a programmable network. And also Mattia and I have a test bed, and maybe KO may have a test bed. We can show that before regulation, you have to show the value to the government, right? So, and also, we have to think about what we could do. 3GPP says that it's optional. There's no reinforcement that you can do. And in this case, we have to build things and show things, and we need this. And in Japan, we do need resilience, because you look at this Mount Fuji, we have to have that, right? But it's very hard for telcos to deploy their base station here, because there's no regulation, there's no law enforcement to do that. Right?
From a policy perspective, when the operators go in front of the spectrum regulators and they ask for more spectrum, the only stick from the regulator's perspective is to provide coverage. The metrics are very, very loose in terms of what that actually means. So to provide coverage to, for example, near the Mount Fuji area, it's based on some density metric, because primarily their market is dense, urban, Tokyo. That's where the majority of the paying customers are. When you come out to such a rural area, when you come out to a very hard geographical terrain to cover, the amount of effort to put in that infrastructure. So you put up one big massive MIMO base station, you radiate very high EIRP, and then you go back to your regulator and say, coverage area done. I'm able to cover about 70% of the population. Life's good. I meet the criteria. Give me more spectrum.
Good. Any more opinion?
Population coverage, of course, important also from the company point of view, but not only, yeah, because we need even such kind of the area. So area coverage itself, so we need, but of course, we need to consider how to make money. And then, so not only just government, of course, we are democratic country. Then based on the people's opinion, that's important. We need to show the importance of these. Then, yeah, $1 per person or something. Yeah, if they consider, so it's very, useful or it's important, then can be accepted. Also, the companies, as I mentioned, so communication, particularly also not only wired, but also the wireless communication. Now the social infrastructure, like a water or like a electric power, then not only just considering the making the money, they have to consider those kind of as the social infrastructure. Then, yeah, we need to show the possibility or importance or of those kind of the things. Then people support or say to the company or government. That's a democratic way. I don't know in the next kind of policy.
So
but-
this is exactly what I mentioned about democratization. Tommaso, you wanted to say something? Okay. So unfortunately, we have 2 minutes left. We speak too much, but Yamanaka Sensei, we have 2 minutes.
Okay, thank you very much for very interesting talk. But our Japanese team emphasize NTN or satellite communication, especially the resilience. But our US and Europe, it's not so much attention for the resilience point of view for the satellite communication, because there is no border, no country, much easier to roam for and communicate with each other. What do you think?
So actually, contrary to your point, NTN is hugely, hugely important. Now, Starlink is something that right now is providing that level of service, but there is a huge amount of work happening on direct-to-device. So some of the work that Nakao-san showed that he's doing with Rakuten, we have similar amounts of work happening. Companies like AST Digital, companies like T-Mobile, Apple, Global Star, they are pretty much players who are working in that space. Now, if you break it down, I think primarily the innovation is happening in the LEO side, but we also have constellations in the MEO and GEO side, and that hybrid network architecture approach, the SAIN approach that you're talking about, that is where there is a significant amount of work that's happening. Now, again, unfortunately, it comes back to the revenue, but it also comes back to your device handset. How many more antenna elements can I stick there for me to have another satellite receiver now? Probably not. So somehow that integration with a 5G chipset has to happen in the future generation. So yes, we maybe skipped over it here, but in terms of the amount of active research work that's happening, it's a very, very active area, similar to what's happening.
Especially, and for sure, no, we've been working on some of these areas related to algorithmic innovation and openness for terrestrial wireless systems. But in recent years at Northeastern, we've started programs on resilient routing, mesh routing between different satellites, as well as on just open RAN and connectivity for non-terrestrial networks. And that's an area of, we think, of huge growth and importance in years to come.
Yeah, I do know lots of activities are going on in US, so it's not just presented today, right? Okay,
Very quickly, coming from Finland side. So in Finland, although we are a small country, we have growing interest to NTN, and there are several interesting startups doing lots of different things. I think our state-of-the-art technologies rely on very cheap, small-size satellites related to Earth monitoring and these spectral analysis or whatever. And actually, next year our university is going to launch our first satellite even. So yes, it's increasing interest area also in Finland.
Yeah, our national strategy importance is APN, all photonic networks, NTN, and advanced wireless. These three things. I skipped my slides there, but I can tell you that. So I think every country has interest and stress importance of NTN. Okay, so now we have to choose between two. One, let people go and we continue for 1 hour, or because some people need to catch train, okay? Or we can, give you 10 seconds each to speak about number three. What is the immediate action that we can take for international resilience activity? Tommaso.
I'll start 10 seconds. I think immediate actions for number three is to do more of number two. So have more collaboration between international like-minded countries. And I think, in this panel, we've seen a great example of that. And I think we need to continue to do that.
Great. That was good.
Consistency, openness. So consistency of message, meaning we are saying the same things across allied and friendly nations, whether it be Japan, Finland, US, or other countries that may be in the room. And then openness, right? Openness in terms of data, openness in programmability, and openness in open radio access systems.
Okay, if I continue. So I think we academics, we have to make sure that this issue is being discussed in scientific fora. We have to keep proposing this to be discussed in different conferences and workshops. And as an example, Aki and myself, we are involved with one resilience-related workshop to be organized in March in Milan at WCNC conference. And another example from my personal perspective, I actually started 2 days ago to write a new big research proposal to Academy of Finland, 6-year project on resilience. So let's keep this topic living and increasingly make noise based on our scientific findings from this. And everybody else will realize that these are actually relevant and good things.
Great.
Yeah. Yeah. Okay, so quickly. So international collaboration through face-to-face meeting.
That's good. We have to do this again. Okay, so from my side, I can repeat what the Matti said. We can keep this topic running, and we will have a workshop in Milan, right? Milan, yeah, that was CNC. Okay, let's do that.
Well, first we have, if you're plugging it, I'll plug our stuff. So we have a resilience panel at GlobeComp in a couple of weeks.
Yeah.
And then we have our workshops. And then Marty, I'll give a shout out to our work that we're trying to do with the NATO Diana effort. And I think there also we're trying to push resilience. So yeah, I think there are many intersection points and we continue to do this work.
Okay, so I think we all agree on the next step. We can meet again and talk about this. Okay, thank you very much for your attention.
And thank you very much for the panelists. Can I call up Professor Yamanaka, President of ICE, to make closing remarks or an overall commentary for today's session?
So thank you very much for attending this conference. I attended this afternoon the half-early part of the symposium discuss about multi-technology. IIC, of course, the largest institute for IT technologies, but IT network telecommunication is not one. The device come to the bottom, and very big breakthrough is often occurred, like a fiber, like a millimeter, and some application now come to the top. And come to the top, and network and the services dramatically change. AI or some new services, vehicle or something. So we need some communication between the in society, in IIC. So please continue this among these discussions in IIC. And I'm also a program officer of the Aspire, the later part of this discussion. So Aspire is a $500,000 per year. Aki takes a big money. So, but it's limited. 70% of the funding must be used for the soft part, not research devices. Soft means go abroad, discuss like this one, and make some consortium, make a team like a rugby. Tomorrow, I'm a professor of the Keio University. Tomorrow, Waseda Keio Rugby. The Japanese rugby team is one team. The many people like here have to make a one team and attack to the future resilient network. That is not a fancy business, but very important for the telecommunication infrastructure. So please continue like this symposium and make a big breakthrough. Thank you very much for coming.
Thank you very much. And last but not least, Professor Nakao for closing remarks.
So we have 2 minutes left. So I like to express my gratitude because this symposium was made possible because of all of your efforts, all the participants from abroad, from domestic regions, and also online, and also especially students and also staff that put together their materials as a poster presentation. And if you have time after this closing panel, please look at these posters. Especially there is medical cyber lifeline work, which is not presented yesterday. So please take your time to do that. And I'd like to again thank you very much. Without your cooperation, this couldn't have happened. So, and thanks Mia for coming all the way from Finland. So this is the democratization approach that I'm talking about. We can invite everyone to make telecommunication better and also more robust. Okay, thank you very much. Let's close the close this symposium. Thank you.